Okay, so welcome back to the last day of this workshop. So today we are going to hit day number 3, that is going to be focus on coupling, detailed microkinetics, and kinetic Monte Carlo simulation with CFD and reactor modeling. Before getting started with the session of today, let me just remind only the fact that the Q&A is handled via Teams, so you cannot use your microphone. You just submit your question through Teams, and then we, as done yesterday and on Monday, we're going to collect them and answer at the end of the session. You will receive the second link. You have already received the 2 links, but we will send you a reminder when you have to switch to link number 2 of the day for the second part. Again, I remind you that the meeting is recorded and the registration will be made available at the end of the online workshop via a notification that we are going to send you via email. All right, that said, let's go now to the day 3. So coupling detailed microkinetics and kMC with CFD simulation and reactor modeling. This will be handled by myself and by Mauro Bracconi from Politecnico di Milano. This is the agenda of today. You have also received the slides that you can download from the link that you can find in the Teams chat. So part 1 will be dedicated to theory and tools. In particular, I will show you our developments regarding the coupling, microkinetic modeling, and computational fluid dynamics, the speed-up techniques that are particularly required to perform the coupling between kMC, CFD, or reactor modeling in general. And also, we are going to give you an overview of the hierarchical modeling of chemical reactor, which is actually particularly useful when you have to go to the industrial scale. Around 3:30, we will have the break and the switcher. And then in the second part, that will be given by Mauro Bracconi, you will see an in-depth analysis and the showcase regarding the applications, regarding the catalytic foam, setup and case studies, and the use of machine learning for the tabulation of kinetic schemes, and a practical example on coupling kMC and computational fluid dynamics. Okay, let's start with the part number 1 that will be given by myself. So in the last 2 days, you have heard a lot talking about chemical reactions, how to model in particular the kinetics of the chemical reactions in several ways. So if you think to the chemical reaction in general, this reaction basically reflects the intrinsic universal tendency of a system to approach the thermodynamic equilibrium. So you start from initial condition, you have a final condition which is actually dictated by thermodynamics. You know that your system somehow will tend to go there, okay? From the perspective of a chemical reaction engineer, however, what is very, very relevant is not only the equilibrium per se, but is actually how we are going to approach this equilibrium, so the dynamics towards the equilibrium, which is basically reflected in the rates of the chemical reactions. So by using and by playing with the dynamics, you can, for example, try to go as faster as possible to the thermodynamic equilibrium, if the thermodynamic equilibrium is the final condition that you want to achieve in the reactor, but on a completely different perspective, for processes that are mainly in kinetic regimes, that you want to use basically these dynamics in order to avoid to reach the total thermodynamic conditions and, for example, stop your reaction at particular, intermediate products that can be of interest. In this respect, catalysis play a crucial role in dictating and somehow, as we will see later, tailoring these dynamics. And in particular, a catalyst can be seen as a functional material with specific active sites, and we know that these specific active sites basically are able to provide a stabilization of the free energy of the different transition state, and therefore are able to drive a particular path from the initial point to the final point in your reactor. The overall rate is, according to the transition state theory, is basically related to the difference in the deep free energy between the transition state, the kinetically relevant transition state, and the reactor where you start your measure of these rates. And in particular, this stabilization is related to, or depends on enthalpy, entropy. So basically, enthalpic content is mainly driven by the composition of your catalyst and by the interaction between the transition state and the material itself, but also on the chemical potential, in particular the local condition of chemical potential that, for example, are related to pressure, temperature, and composition. This means that what you observe in practice is always a multiscale, is the results of a multiscale process, and not only the active sites counts in delivering this final, functionality that the catalyst is able to give you to your system, but also the particular environment where these active sites are placed. This overall environment, we can call it the chemical reactor. Just to give you an idea of this, I want to use quite an important example that comes from industry. So let's consider, for example, this reaction. This is the partial oxidation of orthoxylene to, the phthalic anhydride. And in particular, you know that the total, equilibrium will be to lead this molecule to the total oxidation that will be dictated by thermodynamics, but you don't want to go to the total combustion processes. You want to stop your oxidation to a partial level in order, for example, to get your phthalic anhydride out of the reactor and avoiding it to burn it, for example, to CO2 and water. This actually is realized with a classical configuration. This is one of the possible configurations. It's a multitubular fixed bed reactor cooled by a circulation of molten salts. Now, depending on how you operate it, you're going to operate this reactor, you can have different conditions in your process. For example, you have, this is a classical profiles that you can have in this reactor. You have the temperature profile is characterized by a hot spot, and this is the concomitant yield that you can have in the reactor. Look, for example, now at the, let me just open the laser pointer. Look, for example, to the temperature profile and to the yield, which is actually here reported in the blue, as the blue lines. If you want, for example, to enhance the yield in your reactor, you may consider, for example, to increase the coolant temperature. You see that the hot spot becomes much higher. You gain a little bit of yield, but if you increase too much, you have that the same reactor is going to give you a completely unselective situation, and now you have an unstable situation where you have basically a runaway of the reaction, and then you have basically yield zero, means that you have combust everything to CO2 and water. If you're clever enough, for example, you can think to have a double, bed configuration. This is actually another industrial configuration which is typically used, whereby, giving a proper distribution of the catalyst density along the axial coordinate, you are able to somehow dilute the thermal content of the reaction, and therefore you are able to increase much higher the total yield of the reaction. So to make the long story short, this means, this is actually an important example, that the same catalyst, because this is actually exactly the same catalyst, can actually give you a completely different, conditions in practice, so a functionality of the catalyst, if you want to call it in a more formal way, depending on the reactor environment. And consequently, it is dramatically important to properly tailoring the reactor environment in order to be able to extract or to exploit from your catalyst the best, or the optimum conditions, for example, in terms of yield in this case. So if you want to put this in a more formal way, we can say that we have a multiscale functionality, which is not only related to the catalyst, so basically the specific interaction between the transition state and the composition of your catalyst, so the nature of your active site per se. But also you have the other two scales are great importance. In particular, they are important in the sense they are going to dictate the long way that your molecules has to undertake in order to reach the active sites, and on the basis of the relative rates of these physical and chemical phenomena, you have the overall observed functionality in your reactor, which is an intrinsic multiscale property of the system. Well, in the last, I would say, 10, 15 years, there have been a lot of effort in trying to approach this problem from a first principle point of view. This means that we want to account the two lower scales, so the microscale and the mesoscale that you have seen quite in depth in the previous 2 days of the workshop, to a detailed description of the transport phenomena and the reactor engineering aspect at the macro scale, in order to be able to describe in a rational and first principle way the different scales and the mutual interaction among them. These actually are very important aspect in order to be able to have a rational design of the process, for example, in view of process intensification or in view of the development of new processes and materials for catalytic processes. What is the problem? The problem that a direct coupling is completely unfeasible. One of the main reasons is related to the fact that you have a huge difference, especially in the time scales between the microscale and the macro scales, but also you have a strong interdependence among the different scales. As you can see here, you have a strong interdependence in the sense that your turnover frequency is a function of the condition of chemical potential that are somehow dictated at the level of the macro scale, but on the other side, the relevance of the transport phenomena are related to the rates of the chemical reaction in order to bring your system either in chemical regime, for example, or in internal or external limited regime. So the approach that we consider, and is actually something that you have already seen even in textbook, as I will show you in a moment, is to realize this coupling basically through a sort of decoupling or effective decoupling among the scales. This actually allows you to have a computational efficient formulation of the multiscale problem by somehow, as I will show you in a moment what I mean in practice, realizing an effective decoupling of the interdependencies among the scales. In order to explain this, let me give you the possibility of showing an example, very trivial one. This is actually the one that you have, for example, seen already in textbook materials or in some basic course at the bachelor level. So when you, for example, you consider a PFR calculations where you have an overall rate equation that you plug in for example, PFR plug flow reactor description of your reactor environment, what you do in practice is already this effective decoupling. What do I mean? So if you consider, for example, the fact that you have an overall rate equation, this, for example, can come from a Langmuir-Isherwood Hugen-Watson treatment of the kinetics, you have already made some specific assumption regarding the rate determining step of the process, about the most abundant surface intermediates and so on and so forth, and this that you have done upfront beforehand has ended up in an overall rate equation, and you basically plug this overall rate equation in the transport equations, in the continuum equation at the level of the reactor. Here, basically, this decoupling is realized thanks to a strong assumption that, for example, can be done by using specific experimental information on the reaction mechanism. So basically, rate determining step and most abundant surface intermediates. Another example comes from microkinetic modeling. So here, basically, you do the same, except for the fact that you are not now consider any assumption regarding the rate determining step. Here, what you want to do is to consider explicitly all the rates of the single elementary steps that you try to describe, for example, by the methods that you have seen in the first day, thanks to the lesson given by Gerard and by Dion, you consider explicitly, for example, under the mean field approximation, the rate of each of these steps, and then, thanks to the coupling of these rates with the transport phenomena and the hydrodynamics at the level of the reactor, you are able to consider the effect of the mass action on the different kinetics, and consequently you have in this case that this effective decoupling is realized without any mechanistic assumption, and actually your mechanistic investigation is one of the results of this kind of simulation, as we will see today. Okay, so basically I hope to have convinced you so far that if we want to solve this problem, we need, first of all, to have all the different, ingredients and tools at the level of the single scales. So microscale, mesoscale, and macroscale. And also that we need to properly realize a bridging between these different scales in order to get the observed functionality of your catalyst. Be aware that this actually is very important not only when you want to perform a reactor design. So let's say that you have a kinetics and you want, for example, to have a full design of your reactor by, for example, designing the type of support of the length of the reactor, for example. But it's actually extremely important also when you want to interpret kinetics. So let's say that you are in the lab. In order to get the rates, you need a reactor. You need, even in this case, the possibility of understanding the effect of the macro scale in order to avoid that your investigation of the reaction of the kinetics is going to be biased, for example, by the phenomena that you have in any case at the macro scale in your reactor. So in the last 2 days, you have seen the methods regarding the microscale and the mesoscale. Now, in the first part of my lesson today, I want now to concentrate on the theory, or basic essential theory, that are required at the macro scale in order to make you aware of the type of calculation or the type of equations that you need to solve with the tools that we will show you later today in this lesson. So the macro scale is typically modeled by the assumption of a continuum approach. So we are considering what you have at the level of the reactor as a continuum in space, okay? And consequently, basically, you have to relate to by invoking some conservation principles that are mainly the conservation of mass, the conservation of energy, the total energy, and the conservation of the momentum. How you can very easily derive these equations by invoking this conservation principle. Let me give you first a very trivial example in order to set the stage and set the nomenclature that I will be using for the rest of the talk today. So when you have to write a balance equation, you first of all need to take a control volume. In this case, we are going to consider a microscopic equation, so an indefinite equation. So we have a very simple, infinitesimal domain, a cube of the x, the y, and the z. And now we are going to invoke the conservation, in this case, of mass in this specific dV, which is the infinitesimal volume. So very easily, you know that the mass that you are basically transporting through this volume can be identified to the different flux that you have at the external surface of the volume. You can use the fact that you know the density and the velocity projected on one of these perpendicular direction, and then you have the flux, for example, in the x and x plus dx interface. If you do the same for all the different external surfaces and you apply the logical statement of the conservation principle, so basically what get in minus what get out and plus what is going to be produced in the volume must be equal to the total accumulation that you have in the volume per se, you can actually very easily write down, for example, the derivation of the continuity equation. Here we are going to write the total mass, so we do not have any production term because the total mass is actually conserved. So you have in minus out equal to the total accumulation of the system. As you can see here, you have what is getting in and out for all the different directions, x, y, and z, equal to the total accumulation of the mass in the system. If you now make some very simple math, so basically you are able to linearize the x plus delta x or delta z and delta y in the vicinity of x, y, and z, you are actually able to get the very well-known continuity equation that you have derived by using these simple steps that I just showed you. Now, let me give you a much more important example for today that is related to the application of the same methodology now for the derivation of the momentum flux, the momentum conservation equation that will lead us to the derivation of the Navier-Stokes equation that we will explicitly solve today. We will see some specific example in the second part using the tool catalytic form, but I think it's very important now at least to give you an idea where these equations come from, so you have an idea of what is behind them. So first of all, let's start with this very simple example. So we have a system which consists of, let's say, two plates. At the time equal to 0, everything is at rest. So basically, there is no movement or relative movement between this plate and this other plate. Now, at time equal to 0, I'm going to set in motion the second plate, so the one that I'm pointing right now with the laser pointer. As time proceeds, I have that the fluid gains momentum, and if we proceed, so at the end, we will reach a linear steady-state velocity profile, which is more or less the one that I'm going to show you in the figure. The first plate is actually is kept at rest, so it's fixed. We are just moving the second plate. At steady state, we are going to reach this, velocity profile that is shown over here. Now, if when the final steady state motion has been achieved, has been attained, now the experience is going to tell you that a constant force is required to maintain the motion of the lower plate, this one, at steady state condition. And this force is actually can be normalized with respect to the specific surface or the unit of area. And in this way, you get what we typically call the momentum flux that you are transferring in the system. This momentum flux is basically a clear indication that you are transferring momentum from this point to the other point. And the overall idea is basically that this driving force of the momentum transfer is actually subject to a driving force which is related to the difference in velocity. So velocity gradients are or can be thought as a driving force for the momentum transport. As for example, the temperature, the gradient of temperature is going to be interpreted as a driving force for the transfer of energy, or the difference in concentration or in chemical potential is going to be a driving force for the mass. The driving force for the momentum transfer is related to the momentum flux. Now, if you consider this momentum flux together with the other possibility of transferring momentum in the different relevant surface of my domain, you have the momentum flux, so tau here. Then you have the contribution of pressure, which is another force that you're going to exert on this unit surface of area, so the pressure times your surface area. And then obviously you have the momentum, which is associated with the fact that you have a flow rate, and consequently you have a flow rate that gets in and gets out, and consequently this is subject to the transfer of momentum. So we can actually agglomerate all these quantity together, and we get what we typically call the combined momentum flux that you have in your infinitesimal domain. If now you consider this combined momentum flux subject to the conservation principle, so the one that I showed you previously in the simple case of the derivation of the continuity equation, so basically in minus out plus production equal to accumulation, This is actually a little bit more involved because you have to consider the fact that, for example, the flux of the X momentum has an effect also on the other, part of the domain, but it's actually something that you can get also from textbook material. So the reference here, as I indicated in the previous slide, I would say that is the Verstuad Lightfoot transport phenomena. Now, if you consider all this flux, not only for X, but even for Y and Z, and you consider the principle of conservation by a little bit of derivation and mathematics, and by considering also that in typical applications you have the presence of external forces given, especially in this case from the gravitational force, you are able to derive the equation of motion that I just reporting here in the more concise vector tensor notation. And as you can see, the relevant contributions that you have in this equation are, first of all, the accumulation, so the rate of increase of the momentum per unit of volume. Then you have a specific contribution that accounts from the rate of momentum addition by convection per unit of volume. Then you have this contribution, which is associated with the rate of momentum addition by molecular transport per unit volume, that one that I showed you before with a simple example of the two plates with a relative velocity between them, and any external forces. So in this case, we just specifically focus on the gravitational force that is typically we have typically had in our system here. Okay. Now, if you now consider the Newtonian expression for the tau in the equation of motion that is expressed over here, you ended up in this final equation, basically just substituting this Newtonian expression of tau over here, you get the final equation, which is indeed the Navier-Stokes equation that is subject, or basically the main equation that we will use today in order to basically make you a sort of tour in the coupling between the transport phenomena at the reactor level and the two previous cases that you have seen in the two previous days. Okay, now we have an equation, we need to solve it, right? So, as you may guess very easily, an analytical solution is actually very rare. So there are some cases where you can analytically solve the Navier-Stokes equation. You have, again, a lot of very scholarly examples in the Verstuad Lightfoot that I really suggest you to go through them because are very important to get, a sort of, in-depth understanding of the equation and on the system. But in most of the cases, and I would say in all the cases that are for us with the aim of today of coupling this equation with the kinetics, the analytical solution cannot be found. Therefore, we need to go directly to a numerical solution, and this field is, very widely known as the computational fluid dynamics. So the solution, the numerical solution of the equation that I showed you in the previous slides. So obviously today we do not have the time to go into all the details or all the algorithms possible that are behind the numerical solutions of this equation. We'll concentrate primarily on our developments in coupling this CFD with the reacting systems. What I want to do in the next few slides before moving to the coupling with the reactivity is just to give you some very general messages and take-home message regarding the CFD in general that will be also elaborated later on in part number 2 with some of the examples that you will see. So first of all, what does it mean a numerical solution? It means that the differential equations, the partial differential equations that we are going to solve are in any case approximated by using some sort of discretization methods. For example, finite difference, methods, finite elements, and so on and so forth. Okay. What this means in practice that you are going to discretize on a specific subset of your mathematical domain, this equation, and this leads to a sort of algebraic equation system that now you need to solve. This actually, your computer can solve this kind of algebraic systems because understands something which is finite and not infinite as, for example, a differential equation. And therefore, you have, first of all, the presence of a discretization. Discretization calls directly for the fact that you have to select the domain, and as Mauro will show you later, the selection of this discretization is of utmost importance in order to achieve the convergence of your solution with respect to the discretization. So it would be actually a full nonsense the fact that your final results would be dependent, for example, on the discretization. So you need to check, as we will show you later, the convergence of your solution with respect to the discretization. Another point is actually that discretization is realized by applying your discretization to small domains in space, and consequently, for complex, geometry, this results in quite a substantial amount of number of variables, of a number of algebraic variables, which is the result of the discretization that you need to solve. Okay, this is a result of the discretization in space and time. Okay, and when you have complex domain or complex dynamics, as we see today, this results in a quite computational burden that you need to deal with. Also, typically, in solving this discretized equation, you ended up in using iterative methods, and also the convergence with respect to these iterative methods, or how to efficiently exploit and use these convergence methods is actually very important to make this viable without having too much computational burden. So main issues or main take-home message. So you have a numerical solution. So remember, it's always an approximation. This approximation will count or not with respect to some parameters and some methodology that will be explained to you later. So you need actually to avoid that this intrinsic approximation is going to affect your conclusions, okay? In some condition, okay, even if you are able to solve in a very, detailed and realistic way your equations with respect to the discretization, you have to face also with some other, problems. For example, as we'll see later in the turbulence, we have a specific slides in 15 minutes or so, okay? You have some models to account efficiently for turbulence, and consequently, you need also to deal with the correctness of these models. So even if you have a very, converged solution with respect to your discretization, this does not necessarily mean that your models are correct at the same time, okay? This is actually another important point. If you want, for those of you that are more familiar with the microscale, this, for example, is the same problem that you have with DFT when you are using, for example, a functional. You have an approximation of some effect that comes into the play through a specific functional. Even if you are solving correctly the DFT Conchamp equation, you have the functional that, in any case, if it's not representative of your condition, will lead you to wrong results in any case. As a take-home message, this is actually directly taken from the Fertzigen page, a very useful book if you want to get more details about the computational fluid dynamics, where very easy, in a very iconistic way is going to stress this point that you need to take this into account very carefully in order to perform computational fluid dynamics and not just, color maps that are present on your post-processing of the results. The difference between the two is related, we will give you some example today, on your ability of getting a good compromise between the discretization, the models, and the possible solution of your system. Okay, this actually holds for, in general, a cold CFD, for every CFD. But today, as I anticipated to you, we focus on reactivity, okay? Or how we couple the reactivity with this equation, because just to keep you all on the same line, we want to be able to describe our multiscale functionality of the catalyst. We want to see what happens in our reactor. What happens, for example, in our labs or in our industrial configurations. So therefore, we do not have only the continuity equation and the momentum equation, but we have also the specific gas phase transport of species and energy, okay, which is going to be coupled with, today, by the way, we focus on heterogeneous reactions, but this actually can be used and can be extended also to homogeneous reaction as well, okay, to specific boundary conditions that are going to reflect the presence of the catalyst. So here are just a simple slide that are going to summarize this governing equation in terms of boundary conditions for a mean field microkinetic model. So you have all these reactions, you have the rates of all of these reactions, they result in some specific fluxes at the surface of species and energy, which are related to the specific dynamics in terms of rates of all these different reactions that we have here. What actually this is going to bring in the system? These are slides that are going to summarize very briefly the numerical challenges for these reacting flows at the surfaces. So first of all, the dimension of the system is a problem. Typically, you have in an industrial reactor or in a packet bed reactor, as we see both in the part 1 and part 2 today, quite a complex domain. So means you have a lot of now cells, but also you have reacting systems, and typically you have a number of species which is quite high. Therefore, this results in a high dimensionality of your system that you need to solve on your computer. You have also to face typically a great problem related to the stiffness. So you have dramatic difference in the temporal and spatial scales of your system. And this actually ended up in problems with the stiffness to be handled with. Also, you have the typically surface reaction as coverage dependence activation energies. And this results in a quite important point related to the nonlinearity of your system, and this actually results in a not negligible complication of the solution of the problem that you want to achieve with this reacting CFD of reacting flows. So what we can do and what we have done with respect to the numerical solution. So this basically is the theory behind the tools that we are going to show you today, both in terms of functionality and applications. So typically, not reactive computational fluid dynamics is based on fully segregated algorithm. Okay, this is actually what is behind, for example, standard packages like OpenFOAM or Fluent, for example. These are easy to implement and are computationally efficient. But if you want now to use this algorithm with the particular, feature of handling complex chemical kinetics in terms of, for example, microkinetic models, the strong nonlinearity coupled with the complex domain is going to make this typically algorithm that are used for non-reactive CFD not applicable in our specific context. So what we can do, what are the options if it is not possible? So you can either go to fully coupled algorithm that will be from a physical point of view the most clean and elegant way to treat the whole problem. So you consider and you account for everything at the same time. But however, when you are dealing with complex geometries and complex schemes in a quite substantial high number of species, you have that the computational effort that is required for several for this system basically make this fully coupled algorithm not viable in the first place. Okay. Therefore, what we have taken as an alternative option, and this was the first implementation of the solver catalytic form that I will show you in this part, is to opt for the operator splitting methods, which is actually quite an established, methodologies, I would say, in engineering in general and in chemical engineering in particular. So the main difference between this fully coupled algorithm and the operator splitting is related to the fact that now you do not consider all the different operator or reflect the different phenomena at the same time. You somehow, and I will show you how in the next slides, decouple them, and this has the results that at the expenses of this unphysical decoupling, you can basically treat them separately, and therefore this allows for the best numerical method to be used for each type of term or processes that you need to account for. Let me give you a very simple example just to show you what do we mean with operator splitting algorithm. Okay, our equations very easily can be represented in this way. So we have two operators, one which is going to account for the reaction, and one which is going to account for all the transport, so diffusion, convection, so on and so forth. What you do in practice with the splitting algorithm, you are considering the two different operators, M transport and S reaction, separately. So you see here, in what I call the predictor, I'm going to solve, for example, only the diffusion, only the transport without reaction, and then I have a corrector step where I do solve only the surface, the reaction terms. So the two different contributions are fully separated. So this means, in practice, that if I, for example, have a time span which is Ti and Ti plus 1, so there are two different time steps that I have in my integration, in my dynamics integration that I'm performing right now for my system. At Ti, I start with the predictor, so I'm just basically solving only the transport. I make the system advance from Ti, from the next time step, so Ti plus 1. Then I'm going to solve again on the same time step, now the corrector, without the transport, so now it's fully equivalent, for example, to a batch reactor system. And in this way, we are able to proceed in this, splitting way. So over the same time step, I'm splitting the same contribution, so predictor, transport, and then it's going to correct the solution of the predictor by applying the reaction on it. Let me give you just an example of what you can gain in practice. Okay, there are several gains, several advantages in doing so, several disadvantages as well. We will point out some of this as well at the end of the talk today. But for example, the way you treat the Jacobian matrix is a very neat and clear way to show the advantage of this operator splitting algorithm. So you know that Jacobian matrix is very important in solving this system, in the discretized system, because typically when you solve an algebraic system, you go through linearization, and this actually Jacobian matrix is an essential term for it. Okay, so you have to evaluate most of the time the Jacobian matrix. So in principle, this matrix in the global problem, so reaction and transport at the same time, is sparse, is unstructured, is blocks, and is stiff, because you have stiffness in the problem. Okay. Now, if you consider only the source term, you have, as you learned, for example, in the first day, in the mean field solution, for example, of a kinetics equation, okay, you have that the kinetics depends on the local value. For example, the rate is K times coverage of A local. Does not need any spatial derivatives. So if you don't have any first, second derivative, for example, in your system, you do not have that the solution at this point depends on the solution at the other point. You're not going to discretize by using the information on different domains to get the discretization of the derivatives. Therefore, you have that the source term is going to leave you a very specific shape or pattern of your Jacobian matrix that is typically diagonal and blocks. So you have specific algorithm that allows you to treat stiff system. And remember that the stiffness comes primarily for the source term over here. So therefore you can apply the best method for this specific structure of the Jacobian, and therefore handle very efficiently the source term. On the same time, if you now account the second operator, but without the transport, you have now the transport term is definitely sparse. So basically you have information in one cell that depends on other cells due to the fact that you are discretizing the derivatives, which are important typically in transport, first and second derivative. For example, if you think to a trivial 1D discretization of diffusion and reaction and convection, okay, then you have this sparse and unstructured Jacobian matrix is the classical one that you can have, for example, in the case of a cold fluid dynamics, so not reactive fluid dynamics, and therefore you can apply the standard algorithm to solve the transport term. To make the long story short, the application of the operator splitting algorithm has allowed us to specifically use, a good or adaptive, or better, specific algorithm for the two source term without, having in common the disadvantages that these are going to bring to the reactor and vice versa, to the reaction and vice versa. So the sparsity is for the transport and how to handle this, and at the same time, the source term can be easily handled as a classical batch reactor, as an ODE system, without the contribution of the transport that is resulting in this sparsity of the Jacobian. This actually is this is a very brief overview of what catalytic foam does. These different terms are put them together in an iterative procedure. This actually is behind what Mauro Bracconi will show you later this afternoon with the showcase of catalytic foam. So I'm going to skip this because you will see this in practice later on. Let me give you some additional information related to the capabilities that we have in catalytic foam as well. So originally we started with a laminar flow, okay, so low Reynolds number. So basically, with those of you that are not very familiar with fluid dynamics, basically here you have a very well-defined streamlines, okay. But if you start pushing the velocity and then you increase what is typically referred to as the Reynolds number, you enter in a situation where you start creating vortices that results in a very, fluctuations of the different properties, and therefore you need to carefully handle this situation in order to properly solve the Navier-Stokes equation in the turbulent conditions. So we recently extended this catalytic foam that was originally developed in laminar conditions to turbulent flow. This was done in the context of the REACT Pro project, which is a European project that also Mikhail yesterday mentioned in his talk yesterday. So where we both are partner there together with other people that I will acknowledge at the end of the talk. Okay, basically what we have done here as one of the work packages is to extend catalytic foam to the turbulent conditions. So at the end of the day, what we have done in practice is basically to implement some of the models. Remember what I told you 15 minutes ago. Even if you are solving correctly the discretization, somehow you have some models that are needed to make possible the solution of the equation. This is one of the cases. So the most let's say accurate way would be to perform a so-called direct numerical simulation of the turbulent conditions. That means that you want to resolve exactly these different fluctuations. Okay, this can be done with the equation that we already briefly derived in the previous slides. But this, on the flip side of the same coin, results in a dramatic complexity about the required resolution, both in time and in space, for your system, and therefore this basically become completely not possible from a practical point of view, unless you have very, very simple and well-defined system. Typically, this actually you find it more in the literature of classical fluid dynamics. You have some models to account properly. I don't want now to get into the details, but we can handle this later on in the questions if you want. Like, for example, runs or LESS, or large RD simulation, or for the modeling of this, or properly account for this fluctuation. Okay, this has the advantage that this allows you for a much more coarse grid, and consequently you gain a lot from a computational point of view. But on the other side, your solution strongly rely on the applicability of these models in the specific context that you are dealing with. Okay, therefore, again, this is a clear example where you have to have a compromise between a reliability of your model and the possibility of have a converged solution in a practical time for your applications. Just to give you an example that we have done in the context of this European project, so we tested some simple cases from the literature. This is taken from this paper, Apple et al., Proceedings of Combustion Institute. So we have a catalytic combustion in a channel. Just to make you, to give you a short overview, so we are working at the Reynolds about 15,000. You can see here the solution, or 30,000, 15 and 30,000 here and there. And we have the different solution that we can get as compared with the experimental profile that were measured in this paper between our model with catalytic form and the experimental measurements. But now, if you are familiar with the chemical reaction engineering in general, you know that one of the important pieces of information that are required to be accounted for, especially when you go to industrial conditions, or vice versa, when you want to be sure that your catalytic measurement, when you're measuring the rate, is not affected by transport, is a proper account of the intraphase diffusion in the pellet. So, as you know, this was discussed quite heavily in depth in the first 2 days. You have catalytic sites. This was explained yesterday both by Michael and on Monday by Dion and Gerrit. You want this catalytic site to be available to the flow, right? And therefore, in order to maximize the number of these sites per unit of volume, you try to put this catalytic site as much as you can per volume. This is typically done by using porous metrics that act as a support of your catalyst. You are actually putting your nanoparticle, for example, if you're having a metal catalyst, on the internal porous structure of this support. And now, from a chemical reaction engineering point of view, you need to account for the diffusion and reaction inside these metrics. Why this is important? Because for any reason, the limiting step of your diffusion is going to be actually, of your reaction, is going to be actually the diffusion. Okay, these are phenomena that are in series, so the slowest one will be leading the overall performance of your reactor. In this case, either you are not measuring a catalytic rate, or if you are interested in the design, you are designing your system not based on the catalytic rates, but based on the transport rate. Okay, therefore, it's of utmost importance to account in this long way to the active sites also of the intraphase diffusion. We have done this basically 4 years ago by the detailer related and can be found in this paper over here. And we did this by using a so-called multi-region approach. So basically, we consider 2 different regions in our reactor. So you have the gas phase. This is actually a local view, but you can actually consider this in a random situation, and you have, for example, a packed bed. The gas phase part is the one that I just described to you in the previous slides, okay? So basically related to the solution of the hydrodynamics coupled with the boundary condition in the external part of this catalytic region, which is the catalyst, okay? But now, we are not accounting only of the external boundary through, for example, an effective flux, as we have done in the previous methodologies, but we extend it to the explicit solution of the diffusion and reaction in the pellet, coupled with the microkinetic models. Okay, so basically, this is what has been done in the multi-region approach to this problem. So what you have in this case, you have a resolution of the grid in the solid part, a resolution of the grid in the fluid part, and then we reported in the paper that I referred previously, proper methodologies to handle the boundary conditions, where you have a continuity of flux and species in order to ensure that the 2 different domains are going to properly communicate each other. So what happens, or what you have in the end, that this coupling between the 2 regions are going to give you the real effective coupling between what happens in the gas phase and what happens in the diffusion in the solid region. So you are able to resolve both the streamlines and the concentration concentration profiles in the gas and the concentration profile in the pellets. So today, for time reason, we don't have the time to go into the details of this in terms of practical applications, but keep in mind, for those of you that has some expertise in chemical reaction engineering, this allows you, for example, to get what is typically under the overall subject of effectiveness factor. It's going to tell you how effectively you are able or efficiently you are able to exploit your catalyst. So if you are in an extreme situation where this diffusion is actually very, very limiting, you are entering a situation where, for example, you are not able to exploit 100% the capability of your catalyst. Again, I want to keep this as a sort of bottom line. One of the different ingredients of this multi-scale picture can be limiting, okay? And in this situation, if it does so, you are basically not able to effectively, for example, exploit your precious material or your precious catalyst that you have developed with extreme effort, for example. Let me give you now some showcases, okay, on what you can do in practice with catalytic foam. And then again, this will be again taken and built up from here in the second part of the seminar today, of the workshop today, with some practical example. In particular, here is one of the very first examples. You can find all the details in the paper over here, where we have a string reactor made by a series of rushing ring that you have in the reactor. Today, by the way, you will see with Mauro Bracconi the exact implementation of this case for a little bit a simpler case, just for time reasons, which will be a string reactor made by a series of spheres and not a series of rushing rings. But this is actually very, very useful to give you an idea of what you can do. You go from the detailed accounting of the flow rates and streamlines. You see, you get how the streamlines are going to be disturbed by the presence of the different rushing ring, and then you are able to describe preferential path, recirculation, whatever, okay? You then are able to predict the different concentration or chemical potential, as you want to call it, in the different part of the reactor. So here, for example, is the concentration of oxygen and concentration of water. Is a simple case of a hydrogen combustion in this string reactor. But thanks to the fact that we are using a microkinetic model, you can also go to the detailed understanding of the local situation that you have at the level of the catalyst. You see here, for instance, the fact that you are able to fully resolve the add species at the catalyst as a function of what the catalyst is experiences in terms of concentration in the gas phase. Here, for example, is the OH adsorbed at the surface, the hydroxyl, and here is the atomic hydrogen adsorbed in the different part of the domain. As you can see here, you have variation, and this variation are related. Remember the effective coupling between the different scales, or what happens both at the macro scale, so basically here, and at the level of the micro scale, that here is basically behind the rates expression that are the boundary condition that we have here, and we are solving with the catalytic foam. We can do much more complex cases. Again, I refer to the paper to go to the details. These are actually open cell forms, quite innovative structures, much more complex in terms of domain, as you can realize by simply looking at the picture over here. This structure can be very important, for example, in some part of process intensification. Mauro probably will give you some details on this at the end of the part 2 today, okay? But also, this is actually a classical and traditional, packet bed. Here you have a packet bed of cylinders. Here was a simulation using the methanol synthesis as a reaction system. As you can see here, we can go from the streamlines, the different gas phase maps and temperature maps, but also you're able to resolve what happens inside the different domain, in the different particles. So because we are running the multi-region approach, and later on you are also able to get a resolution of the different particles. So you are not treating this one for all, but you are solving all together the hydrodynamics along the reactor, and consequently you can understand whether a particular pellet over here behave in a different situation, and this actually opens new ways, for example, for getting a more detailed analysis, but also open the stage, for example, to use this kind of information at the reactor level to have a rational design of the operating condition or of the reactor conditions. Okay. All right. So far we have seen, just to keep everything under our attention, so to keep all of you on the same line. We have seen that we need computational fluid dynamics, okay, to have a detailed description of what happens at the level of the reactor. This is important because if you want to see how your catalyst is delivering to you the observed functionality, this observed functionality is somehow dependent on the reactor environment that you are tailoring at the level of the reactor. We concentrated so far our attention to one specific case, which is the fact that these pellets do not move, right? So probably I didn't specify at the beginning, but these are fixed by the reactor. I think you are familiar with this. Also, if someone from that has more expertise in experiments, this is actually what you typically do. For example, in a lab, when you are getting the kinetics, you have a powder reactor, you have an annular reactor, or whatever, but typically you have a situation where you have a fixed catalyst, and then you have a flow rate that goes through this packing thanks to a specific pressure drop that you are superimposing to the system to make possible the flow rate that goes through the packing. Okay. However, this is not always the case. Okay. Especially, there are some important industrial applications that make use of a variation of with respect to what I've shown you so far, that I'm now briefly introduced because it's one of the latest development in the last 2 years of catalytic form. So these are just to give you an idea of what we are talking about right now. I report here what is widely known as the ergon equation. The ergon equation basically tells you the pressure drop that is required in order to get a specific flow rate, okay, if you want. So far, in the method that I showed you in the previous slides, we didn't use the ergon equation because the solution, the Navier-Stokes equation, is going to give you again the delta P. So the ergon equation is a simplification, if you want, of the momentum equation from a macroscopic point of view. But the point that I want to make now that when you have a pressure drop, so pressure here is higher than here, in order to make possible that I'm able to flow something from here to here, you know that you have a pressure here and a pressure here. Let's suppose now that the area here is equal to the area here. If now I have pressure times a cross-sectional area, pressure times a cross-sectional area, the area is the same here and there. The pressure here is higher than here because I have a positive pressure drop. Now I have a force, a net force that is pointing in this direction. Okay? But why so far we didn't bother about the presence of this force? Okay? Well, this actually was because the weight of the particle itself were enough high to counterbalance this force, and consequently these particles remain fixed because the overall flow rate, the overall force that was acting on the different particle was basically zero. Therefore, there was no movement since you start from at rest, right? But now what happens if I'm increasing the velocity? Let me just go back one slide. If I increase the velocity, this is actually what can be inferred very simply from the ergon equation, okay? You have a higher pressure drop, velocity here and velocity here, right? Therefore, there is definitely a limit that we call the minimum fluidization velocity that is realized when the drag force, so this net force exerted by this pressure drop, is equal to the actual weight of the particles. If now I'm increasing this velocity beyond this minimum fluidization velocity, I have that my particle starts to fluctuate in the domain. So the particles are no longer fixed. They move in a chaotic way. They do not go away because still we are far away in order to basically go beyond the free fall velocity of each particle that will lead basically to empty basically the reactor. But if you stay at the level of the minimum fluidization velocity or higher, somehow higher than minimum fluidization velocity, you enter a new way of handling the reactor, which is called the fluidization, the fluidized bed reactor. These are very important reactors, for example, in industry. Some of the selective oxidations are performed in fluidized bed reactor. Other types, of, for example, that consider a very important the fluid catalytic cracking system, which is one of the main, processes in the petrochemical industry, behind, for example, our daily consumption of gasoline, okay, of good gasoline, very high octane number, okay. These are performed somehow with this concept, so much more elaborate complex, but the basic is related to a fluidized bed reactor. Therefore, thanks to the thesis of Riccardo Uglietti, we started this topic in this catalytic foam project. We started from the most detailed way, an affordable way that is possible at the moment. So the CFD coupled with the discrete element method. So basically you are resolving somehow the different particles by accounting with specific model the interaction among them without having a cell that is specific to the different particles, but the details you can find in these two papers over here. What we have done is basically to extend our operator splitting algorithm and other methods to the possibility of accounting microkinetic models and in principle kMC simulations with this kind of fluidized bed reactor. So we have no time today to discuss the detail of the algorithm. For those of you that are interested, the details are in the two papers that I refer here in the slides. But let me give you an example. I hope that the movie is displayed also on your screen. Okay. Here you have an example of what is fluidization. So you see here that I'm supplying my flow rate at the velocity which is higher than the minimum fluidization velocity, or the condition where the force exerted by the flow rate is higher or equal or higher with respect to the actual weight of the catalyst. Now the particle do move inside the reactor without having enough momentum to go away in the up to the freeboard of the reactor. You see that you reach a completely different, way of operating, completely different environments, again, of your catalytic material, and this will result on completely different situation, for example, in terms of reactor environment, and consequently different functionalities. Fluid catalytic cracking is an example where, for example, you have a problem related to the deactivation, and thanks to this you can recirculate the catalyst and continuously activate it. So basically you are able to avoid a fatal condition of your catalyst to getting deactivated along the streamlines that you are operating, or a selective oxidation, you are able to efficiently, for example, handling the hotspot and avoiding, for example, to go in unselective conditions. But again, the details are here. So the bottom line is in the catalytic foam framework now we are able to handle and to achieve this kind of simulations. So now basically we have reached the first milestone of today's presentation. So this is the overall structure of catalytic foam. So we rely on open foam. So we are basically a solver open forms. We rely heavily on the infrastructure, as you can find in the documentation that you can find on the website or on the specific papers cited over here. We are able to get all the kinetics in terms of heterogeneous kinetics, both kinetic Monte Carlo, mean field, and rate equation. We are also able to handle, thanks to the collaboration with the group of Alberto Cuoci, the homogeneous part, so basically the gas phase reaction, and we are able to make possible the interaction among the two. And also, as I will show you later, because I didn't present yet this part, we're able to use specific algorithm to extend it to kinetic Monte Carlo simulation and in general, speeding up techniques that are required later on. Okay, I would propose now to make a 5 minutes break because now we have a different subject, so you can a little bit relax for 5 minutes, and then we will continue, I would say, at 2:20 p.m. GMT +2 with the second part where we'll start handling speed up techniques, kMC, and the description of the tools before then switching to the second part and the second link. Please now remain on this first link. Okay, so remember you are staying on the first link. It's just a break of 5 minutes, so 2:20 p.m. we will start again, and remain on this link. So we are going to talk in a moment. Okay. Okay, so we can start again. So let me again to share my presentation. Is this working? Okay, we're slide 85. Okay, so we were basically here. Can you confirm that you can see it properly? Okay, thanks. Okay, so with this infrastructure, so catalytic foam, you can, in principle, simulate and make a proper analysis or design of any reacting flows at surfaces. That means, in principle, you are not limited from, for example, the complexity of the domain or the complexity of the kinetics. But indeed, you are. Okay, you can easily imagine that you have a very complex domain. You will need a lot of information and a lot of specific handling related to the meshing. Okay, and consequently, a computational burden related to the solution in these parts of the domain. If you have a reaction, you know that it is possible, but you have a very complex kinetic schemes, then you result in a dramatic computational burden related to that. In particular, and this is the subject of the rest of my talk today, if, for example, you are going to evaluate the specific computational time that you are spending either from transport or chemical step, you see that the introduction of the detailed chemistry, so in particular, insofar microkinetic modeling, we will see kMC later in this presentation. The computational burden is actually 90% of the overall time that you have in the simulation. So you have a substantial increase, substantial worsening of the situation in terms of the computational time. And now this can become a not negligible bottleneck that, for example, can make impossible to handle complex cases. Therefore, our effort now is to try to lower down this contribution to the computational burden of the simulation in order to make possible the simulation either of complex schemes or complex geometry or both at the same time. This indeed calls for speed-up techniques. So basically, the idea is that we want to reduce the computational time related to the chemistry, obviously not with simplification of the chemistry, but with some clever way to handle the computation of the chemistry. There are several ways that we have attempted and succeeded in the last 3-4 years. The first one is use a classical tabulation adaptive techniques, the in situ adaptive tabulation, the ISAT, which we motivated basically from the world of the combustion chemistry, and we specifically adapted to the case of dynamic simulation of reacting flows at surfaces. Then we have a cell agglomeration algorithm that we started specifically for the steady-state solution of CFD with microkinetics, and now we are extending also to dynamic simulation. And the one that will be very relevant in the case of the kMC, and will be most of my presentation today, will be on the pre-computing the rates and interpreting them. This is an extreme case, as I will show you in a moment, of decoupling the scales that you want to solve at the same time. Let's start now with the ISAT technique. Here, I want to give you an overview of how the adaptive tabulation works. So in the general framework of the operator splitting algorithm, you have, as you may remember from the predictor and corrector that I show you in the presentation of the operator splitting algorithm, you have to solve along the way, so during the simulation, quite a dramatic amount of ODE system, which is basically the single contribution of the chemistry in each of the cells along the times. Okay, so basically you spend a lot of time by solving ODE system while proceeding in time and for all the domain. However, as you know, an ODE system, the solution is dependent, Cauchy problem, okay, on the initial condition. And it happens by the intrinsic nature of the system that you are solving, that these different ODE systems are not that far, or are not always that far in terms of initial condition, okay? So the idea is actually how we can exploit this information, exploit and storing this information to somehow avoid the direct solution of one ODE system along the way. So basically the idea is I want to avoid one of these ODE as much as I can, and I want just to, rather than solving directly, make use of a history of the simulation in order to avoid the solution and therefore speed up the simulation. Let's see how does it work in practice. So at the beginning, obviously you don't have history. So you have the blank page, and therefore you have nothing else than the opportunity and the possibility to integrate your system. For example, let's say that this is one of the initial conditions, the ODE 0, that you have in one of the cells. You don't have history, then therefore you have just to make a direct integration of your system. What you do now is you define a so-called ellipsoid of accuracy, which is more or less, just to give you an idea, then the details are in the paper that was in the previous slide, and I will show you later again, is a sort of interval of confidence where you think that every point that belongs to this area more or less behave, roughly speaking, as these initial conditions. Means that what you can do later on is basically using this information to predict what will be the outcome if your initial condition, falls within this ellipsoid of accuracy. Now let's do that you proceed. Let me activate the pointer. Let's make that you proceed. Now you have another initial conditions. This actually falls outside the ellipsoid of accuracy that you have set according to the particular tolerances that you have decided in the first place. This is not belonging to this region, therefore nothing else, that you integrate again, so no other options. You have to perform the direct integration from this initial condition to the final condition. But what you do now is to start to collect this information. You have another ellipsoid of accuracy, and you store this region with somehow the final condition that you have just predicted. So basically you start to build up what is called a storage table as a sort of a binary tree that you are building up. Now you proceed again. This again falls in not within any of the previous ellipsoid of accuracy, so nothing else that proceeding in this way. Now you are going to evaluate again your ellipsoid of accuracy. You perform the direct integration, and now you store again the information. At one point, as you proceed along the simulation time, by the nature, the specific nature of the problem, you will end up in a situation where your initial condition now indeed falls within the ellipsoid of accuracy, in this specific case, in this red ellipsoid of accuracy. Now, according to the Isaac principle, you have already, because you are considering everything that falls within this ellipsoid of accuracy equivalent to this ODE 0, okay? Now you can, rather than perform the direct integration, you perform a linear approximation of the final solution, and in this way you are able to retrieve directly the information from your binary from your binary tree. In this way, you have skipped now the direct integration, and you are going to perform a very easy and very computational costless information that you need then also to account for the time that you spend in searching for the information. At the moment, avoid this time. This is typically much less computationally intensive than the direct integration, and therefore you have skipped one of the intensive part. There is another possibility, which is not only the trivial, but is the following one. Let's say that you are in this situation, so the one that I'm pointing right now, is not within the ellipsoid of accuracy of the green solution over here, but is very near. Okay, this is actually more or less subject to your initial choice of tolerances for creating this ellipsoid of accuracy. Now, in this situation, what you do? You have to do the direct integration because you are outside the ellipsoid of accuracy. However, you say, okay, since I'm nearby, let's see what would have happened in the case of a direct integration, okay, of a linear interpolation. You do now the ODE linear interpolated, and you have the ODE solution due to the direct integration. You can actually make a comparison between the two. If this differences is below the tolerances that you have set, then you can say that even this part of the region is going to deliver to you an ODE system that can be given by the linear interpolation of the information that you have already. And in this way, you are able to grow this ellipsoid of accuracy, and consequently, you are able to exploit as much as you can the previous history of the simulation that you are storing in the tree. In practice, this can result in quite remarkable performances. Here is an example of a packet bed of spheres, okay, for steamer forming conditions. You have roughly 80 surface reaction and 13 adsorb species, which is the main dimension that you have to account for in the case of a heterogeneous kinetic scheme. What you have that the simulation speed up is quite substantial, about 15 times faster. You see the decrease of the computational time with the ISAT as compared with the direct integration, so by skipping the ISAT. And this actually can make affordable very, very complex industrial conditions that would have been tackled by using a direct integration. As you can see here, just as a side note, but then the details can be found in this paper over here that you can directly download by clicking on the link here. You have that this speed up is actually changing continuously with different plateau and different behavior as you proceed with the simulation time, because these actually reflect two different things. At the beginning, you have the fact that you need to build up a history, so you cannot exploit the history if you don't have history of integration, okay? But also, at some point, you will reach a point where the time that you spend in order to get the binary tree information out of the tree can become limited as well. So with some sort of techniques that, again, you find explained in this paper over here, you can decide, for example, which will be the best choice in terms of drop and clear the binary tree and, again, start from scratch. This is a sort of best practice in performing and applying this ISAT algorithm, and this is actually explained in the paper over here. Another speed up technique that we basically perform in a collaboration with the group of Anthony Dixon in the Foster Institute of Technology, Politecnico Institute in United States, okay, in Massachusetts, is to use the cell agglomeration algorithm. We started this by reasoning and by thinking to the specific problem of, or the specific nature of the equation that you have by using a microkinetic model in steady state. So this actually is a schematic of the possible concentration, the schematic of the side fraction profiles that you have in the different region of the catalyst. These are, for example, a schematic of a particle in a fixed bed reactor. You see that the same color means same concentration. What you do now, without any other methods, is actually for each of these cells, I'm going to perform my integration. I have a lot of cells because I have a complex domain, and consequently, the number of cells that I have, the number of ODE that I have to solve is proportional to the number of cells that I have into the domain. However, here you're solving again an ODE system, okay? So you can again make use of the fact that most of these cells have in common the same initial conditions. So in particular, if I try to change the perspective, and in particular, I try to, rather than look at my system in terms of different cells, but in different initial conditions, so I try to group the different, colors in sort of bins where I'm going to group the different colors. Obviously, the resolution of these colors will be actually proportional, as I will show you later, to the accuracy of the methods as well. But let's say that by a specific refinement or specific threshold, so plus minus a side fraction, okay, a certain value of side fraction, I'm going to group these colors in different bins rather than cells. You may imagine that by the intrinsic nature of the problem, the number of cells are much higher than the number of bins, okay, because these are related to the complexity of the domain. These actually are related basically to the physical variation of the particular quantity in the simulation. If you do so now, we have a change of perspective. Rather than to solving all the different systems, I just to solve all of these systems once for the different bins, and then I input this information back in my overall simulation. This is actually what we have done. Here you see, for example, just to give you an idea of the accuracy, a solution in terms of OH set fraction without any binning, so without applying this cell agglomeration. Then we are considering two different tolerances of building up these bins. So the way I'm going to group these colors in the different bins. Obviously, if I'm increasing the tolerances, if I'm decreasing the tolerances, I have a much closer situation to the not bin solution than with respect to the one where I'm using a much coarse tolerances for the agglomeration. And these two quantities actually are related to both the accuracy, so the more bins I have, more accurate I am, so less error, but on the other side, more bins I have, less speed-up factor I realize in practice in my simulation. Again, everything will be done or will be designed by considering a trade-off between the error, which will be related specifically to the accuracy that I want with respect to my simulation, or I can consider with respect to the nature of the variable that I'm going to represent, and the speed up. Again, this comes back to my introduction. So we have a trade-off between accuracy and discretization and computational time. Okay, now let's move to another specific part which is very relevant here because will be used for coupling the kMC in the reactor simulation. And is actually, if you want, an extreme case of decoupling the interdependence of the scales. And in particular, we are so extreme that the philosophy behind this approach is actually, let's calculate all the chemistry beforehand. So I want to create, by using a sort of region of interest of variation of the different variables in my system. For example, the temperature will change from this value to this value. The concentration of CO is expected to change from this value, and so on and so forth. By setting this, different region of interest, I can now sample, calculating basically the different turnover frequency in this domain, which is a multidimensional domain, quite not trivial. I will come back to this in a moment. And then by using this sort of data pre-computed, sort of big data pre-computed, because it can be quite a substantial number of data if the dimensionality of the system is high. And then I can use either interpolation like spline interpolation, or as I will show you for most of the time later, using machine learning in order to interpret this data and to build up a surrogate model that will be used during the CFD simulation or the reactor simulation. This actually was a concept, especially the one with the spline, that we proposed originally, roughly 6 years ago, together with a group of Castell Reuter. So the original publication is here, is in SES Catalysis, where we use this plane interpolation to couple kinetic Monte Carlo with CFD simulation. So in that paper, basically what we propose was in order to couple the continuum equations with the stochastic equation that Michael showed you yesterday, what we do basically, we pre-computed the turnover frequency. So the data here, the raw kMC data are the square points here. And then we try to build up a surrogate model. So in this case, a modified Shepard interpolation that is able to represent the variation of turnover frequency with the different variables. So in this case, it was very easy. I mean, easy, it was much more affordable because it was a simple case with only 2 species, okay? And therefore, everything was represented in terms of CO and oxygen. The idea is actually now, I'm reaching at a certain point in a simulation a value of partial pressure of CO. I do not have now to perform my kMC simulation because I did it already once. I just to interrogate my surrogate model or my Shepard models, my polynomial model, for example, this partial pressure, and I directly get the value of the turnover frequency that I will use in the solution of the mass balance coupled with the Navier-Stokes equation. If we go now with a higher dimensionality, the use of this interpolation method becomes a little bit cumbersome and difficult to handle. Therefore, what we proposed, and this is a very recent paper, is a chemical engineering journal that basically was published, was accepted last month, and will be published in this issue in October, a chemical engineering journal, to use machine learning, in particular by using some suggestions given in the literature by the group of Dixon, random forest algorithm, in order to create the surrogate model in the case of high dimensionality of the kinetic scheme. Let me give you an idea on how it works, and then Mauro Bracconi in the second part will give you a practical example of this by showing the algorithm in detail with respect to a showcase. So machine learning is able, by construction, to efficiently tabulate existing data and to provide an accurate and fast prediction of target quantities that in this case are for us turnover frequency as a function of the different dimensions that I have in my system. In particular, in this work, what we have proposed is to use a random forest as a particular algorithm for this methodology, machine learning methodology. Because random forest is a methodology, a machine learning methodology that can treat very easily an ensemble of regression trees that are trained using our build-up knowledge of calculation of turnover frequency. By the construction of this random forest, the algorithm is particularly suited for application with a large number of data, like for example, a complex kinetic scheme. Complex, I mean, with a high number of dimensionality, for example, CO, hydrogen, CO2, water, methane, so a lot of species that you can consider during the simulation. And also, there is some particular feature of the random forest that will be also explained by Mauro in this application. For example, the fact that it can give you some important information, for example, related to the variable importance, and this allows you to highlight the effect of each variable for the final prediction, and therefore it is much less prone to the sensitivity of the hyperparametrization of the surrogate model. The main idea is basically then you're going to have your raw data. For example, let's put it in the context of the kMC in order to link to what Michael has presented yesterday in day 2. You know that this variable on temperature will change in this specific region of interest. You have this hyperdimension, space that you are going to build up and then you have to, all of these points of the hyperspace, you have to calculate the turnover frequency. So you need for once to calculate the turnover frequency. So you have quite, you can imagine that by increasing the number of independent variables, this number can increase quite importantly. You interpret this by using the random forest algorithm, and you are able now to have a mapping of the turnover frequency space now as a function of the different independent variables that, thanks to the random forest, is represented with a surrogate model. So now, if I want to get this specific turnover frequency in this domain, I do not have to perform a TOF calculation with the kMC. I have it done once, and consequently, I just take it from the tabulation, from, in this case, from the random forest, and then I'm going to feed it directly in the CFD or in general in the reactor modeling. Let me give you an example in terms of, for example, CO oxidation on ruthenium oxide. Okay, we use basically the Zacros algorithm, the Zacros package for the kMC, the one that Michael presented yesterday, and the reference are the ones that he gave yesterday to you. What we've done here, we have CO oxidation, so a simple case. We are going to sample at a given temperature CO partial pressure and CO and oxygen, sorry, partial pressure, and for each of these points, we are going to calculate the corresponding kMC simulation in order to have the estimation of the turnover frequency. We use then random forest, and now you have from this, discontinuous or scatter or mapping of TOF as a function of CO and oxygen, we have a continuous representation in terms of random forest surrogate model. The accuracy is good. I mean, depending on how you are able to build up this turnover frequency with the random forest, but you see that all the details are in the paper that I showed you before. But by using different error threshold, you have it is a parity plot, basically a very well representation of your Monte Carlo representation, turnover frequency, and random forest interpreted turnover frequency. If you now put this in a reactor simulation or in a CFD simulation even, you have a dramatic, speed up factor. Here was around 10,000, only because you are skipping, the very, very expensive, just recall what Michael Stamatakis showed you yesterday, the direct kMC simulation during the proceeding of your CFD simulation. However, there is a important point, that is one of the main outcome of the paper over here. Now that we have done this example, let's now to have a specific look at what we have calculated. So here you have oxygen, here you have partial pressure of CO, right? And since we have divided that, because we didn't know the shape of the turnover frequency, we have divided evenly the different partial pressure span between minimum and maximum. You have now that you have a region of this turnover frequency, especially this one that I'm pointing now with the pointer, where basically the turnover frequency doesn't change. But in any case, I have calculated this several times. Okay, I have allocated a lot of points in a region which is insensitive, where the turnover frequency is insensitive with respect to the variation of the two independent variables in my system, CO and oxygen. Therefore, basically, we have that all these calculations at the end were useless, because the information could have retrieved somehow by proposing and by using, and this is what we have proposed in the paper over here, a proper design of a training set. Why this is important? Because for a CO oxidation system, this actually, you don't care that much. So you can do it in a certain, not limiting time a sampling of this turnover frequency. So you don't waste that much time in terms of absolute time. But try to see this problem in terms of a higher dimensional system. water gas shift, to name a few, steam reforming, partial oxidation, where you have more variables in the system, where you want to account for the effect of temperature, and so on and so forth. This can become quite an important problem because I want, in any case, to minimize the calculation of kMC that I require. Because otherwise, if I just use my blindly approach of evenly divided the partial pressure span, okay, I can easily end up in a situation where I spend, for example, a substantial amount of time that could be days, weeks, or even months, if you are make some, back-end envelope calculation with a very high dimensional systems, just to have the data that I need to calculate. Okay. Therefore, an important point is to get a design procedure to have a design of the training set. This is actually what we have done in this paper, and this is what I'm going to present you now. So let's again stick on the CO oxidation on ruthenium oxide. The idea is, let's start with a few points. So since I need to start somewhere, I start with the minimum number of points that I need. The idea is I can start with a few points, and the selection of these points will be shown later in the application in the part 2. But on the basis of these points, I can, in any case, start giving an estimate of the first and the second derivative of the turnover frequency with respect to these independent variables, and try to understand, on the basis of this first and second estimated derivative, how the turnover frequency is going to behave in the different region of this space, or in principle, in a multidimensional space. You need to set a threshold where actually you need an estimation of the error. This error you want to must be minimized, and therefore you are starting to allocate more points where the error is higher. Just to give you an example, here you have all the points are now sensitive, so basically you have a huge error at the beginning, so basically you add point everywhere. But if you proceed now, you see that according to the threshold that you set in the simulation with respect to the estimation of the error, you are going, at the end of the day, to allocate more points nearby the region where the turnover frequency sharply changes as a function of CO and oxygen partial pressure. The final set that was designed in this way is see an accumulation of points nearby, the region where I have a sharp variation of the turnover frequency. You see that by increasing the points, so for 9 points, 72, 140, by this allocation method, the error is going from 400% till 12%. Now, let's make a comparison with a more complex case. No, the more complex case is the water gas shift on rhodium. This actually not, we use as an example, not a kMC simulation, because we can apply this methodology, both random forest and both training set design, even for the approximation of complex microkinetic models. So whatever you're gonna feed in terms of raw data, the algorithm, we are going to tell you how to interpret the model, so the random forest surrogate model, and how to build up the design of the training set. Okay, here we have water gas shift, and the gray points. The gray is the use of a evenly distributed points equal to the number of points that you can read from the y-axis, from the x-axis, sorry. And here on the y-axis, you have the average benchmark error. Let's say that, let's just follow now the evenly distributed points, so without using the training set design. In order to get a threshold of, as an error of 2.5%, so the dashed line that I'm indicating right now, I need to go roughly to 35K, so 35,000 points that I need to have. So means, in this case, 35,000 estimation of turnover frequency using water gas shift or using microkinetic model. But if this simulation or this turnover frequency were calculated from a kMC, this is what, by the way, we are doing together with Michael in the context of the React Pro project, you would have required here 35, roughly speaking, let's say 32,000 kMC calculations to get the turnover frequency estimation needed from random forest to give you a error of 2.5%, okay, with respect to the target accuracy. Let's see how the proposal, what we have proposed in terms of design of the training set, what happened by using this adaptive design methodology. You start here, so with the same number of points, so at the beginning they are still evenly distributed, but now we allocate these other two set of points by using the methodology based on the estimation of the error based on the first and second derivatives. We want to see where the turnover frequency is sensitive or not to the variation of the variables. Here you have more than two, so you have CO, water, hydrogen, CO2, and temperature. Okay. You see that you reach the target point, so 2.5, with roughly 5K calculations, so 5,000 points. Here was basically only 5,000 estimation of microkinetic models, so costless. But if you now try to mutuate this, as we are doing right now in the context of React Pro, to applying this to kMC, the comparison is 35, roughly speaking, 1,000 kMC calculations versus, roughly speaking, 5,000 calculation of kMC to get the same, benchmark error in the simulation. Okay? As you may imagine, this results in a substantial amount of a substantial gain in the computational effort, the computational burden that you need to do with the aim of coupling this kMC with respect to the CFD or reactor modeling in general. This basically here, we are just comparing again what happens if you want to get the same target error with evenly distributed and design and with the procedure for the design of a training set, and these are the detail that you have in terms of operating condition that you have set and the different gain that you can get in terms of evenly distributed versus training set design. So at the end of our developments, you see that differently, or this is the additional point that you can see with respect to the slide that I already showed you at the end of the first part. Now we have this additional module in catalytic form, which is the chemistry speed up, which consists of ISAT, CA, and all the framework of machine learning that we started recently with the paper that I show you, so we just published with the Chemical Engineering Journal 2020. And for us, this will be an enabling point, an enabling tool to make all this framework applicable in terms of complex kMC, and consequently to make kind of an important step forward in bridging the scales in the effort of having a first principle description of the multiscale problem in heterogeneous catalysis. However, even if now you have this nice infrastructure, these tools, and you want to say, okay, I want to use this, I'm going to go to the Catalytic Form website and go to the GitHub, as we'll show you later, and download it, and I'm going to use it. You cannot do whatever most probably you have in mind to do. Let me give you an explanation with an example. Let's say that now you want to handle a complex new case. micropacked bed reactors. So this is an innovative, let's say, reactor technology that is considered in some aspect of process intensification. Okay, we don't want now to enter in the details of this, but the main idea here is to exploit the high static conductivity of the honeycomb matrix coupled with the high dynamic conductivity plus all the advantages in terms of catalytic loading, for example, of a packed bed altogether, for example, in order to smooth the temperature profile in a packed bed reactor in a selective oxidation. Well, you want to do it, you want to use it, now this framework to understand and to develop a real reactor design of this tool, of this equipment. Well, let's say what we have to do, okay? Well, I have channel roughly of 2 to 4 millimeters, filled with spheres of 400 to 800 microns. So tiny stuff, okay? Means if I have to mesh it now, and I want to mesh with a sufficiently, high resolution to be able to track the changes of the different variable of interest in the domain, very easily, let's say with really a back on the envelope calculation, you ended up with a number of cells which is of the order of billions, okay? This actually, even if you have whatever the speed up that we can sell it to you right now, you're not gonna able to get it done in a practical way. So basically this problem cannot be handled directly. So by taking the full scale and feed it directly to your CFD, reacting CFD models, is not actually to be practical because you have a substantial amount of time required, basically is not possible. What we can do is basically the limit of the state of the art, or there is a way where I can use the fundamental understanding that this first principle multiscale modeling from atoms to the reactor can give it to me in order to develop somehow a knowledge about the system and therefore to proceed with the rational design of the system. Well, you can do it, and you can do it by using what we call the hierarchical modeling for the reactor analysis. So the idea is somehow, if you want, simple. So basically, if you try to put in a pyramid view the different models, so fundamental modeling basically is what we've done and what I've presented so far. 1D lamp modeling will be basically what you do simply at the level of the macroscopic equation. I will give you some example of application later in the tools section, but this is just to make and to name some models. I don't know, a PFR 1D model of the reactor, a PFR pseudo-homogeneous model, a PFR heterogeneous model. So strong simplification regarding the equations. Basically, you are not looking directly at the infinite volume, but you look at some macroscopic pseudo-homogeneous representation of the model. And this actually is very much affordable, even for the models that are, for the reactor configuration that I just showed you with the microchannel packed bed reactor. The idea is here. I want to use this by applying the fundamental multiscale modeling on specific part of my equipment in order to derive local surrogate parameters that are then used in the macroscopic, treatment of a modeling of the micropacked bed reactor. Let me give you an example that I think is going to be more explicative than this overall explanation. So if I look at my matrix, I have several contributions, right? I have the honeycomb matrix, where I can identify, for example, as a leading parameters, the conduction in the solid part, the basically the interaction between the particle and the gas in the channel, and the phenomena related to the interplay, the interface between the internal part of the channel and the particle. Okay. Now, if I look and if I focus my attention to only the specific part of my overall equipment, right? Now, this problem is achievable because I do not need to have all the other channels, for example. This problem is achievable because I can focus on some part of the micropacket bed. This is actually can be done, is affordable because I don't have any longer the packet bed, okay? I try to focus my, methodologies on specific part of my reactor. In doing so, then, I try to use all these pieces of information that I'm able to get apart, so using a specific part of my domain, to build up a hierarchical derived, so hierarchical because I'm importing the multiscale CFD-based analysis through a lower level derived model, and then this hierarchical 2D macroscopic model is easily employed as, for example, you do today in classical reactor configuration, in order to get the full description of this and design of this reactor technology that in the first place wouldn't be tackled using the full multiscale approach. This is what we've done. I mean, I skipped the details. You find the details in the publication over here. Basically, here we are able to get a direct, comparison between the temperature profile that you have in a classical packet bed to a temperature profile that you get in this micro packet bed configuration, and then you can use this, for example, to explore the different, operating conditions that you can have in the reactor, in terms of coolant, in terms, for example, of the diameter of the tube, in terms of, orthoxylene to oxygen ratio, and so on and so forth. But you can, with low computational cost, explore in a quantitative yet, fundamental way, analyze a very complex system like such as this micro packet bed reactor that again wouldn't be affordable with a full multi-scale CFD simulation. This actually, in my opinion, is very relevant in the view also of designing experiments, okay, for getting new correlations, because you can actually skip some of the initial experiments or to make a few by a proper integration of this design of experiments with a real programming and design of experimental campaign to get, for example, coefficients or Sherwood number or Nusselt number for, any reactor configuration of some sort that you can imagine or identify in your research or in your business. As a side note, for example, very recently, with together with Dion, with a group of Dion Blacos, we have proposed a similar approach using machine learning. This is published in Reaction Chemistry and Engineering 2020, where we use similar approaches where we combine machine learning, our CFD simulation, and their expertise also in the experiment of two-phase fluid dynamics, in order to, for example, propose correlations based on the design of experiments through these methodologies and machine learning methods. The last piece that I want to show you very briefly before concluding this part and then moving to an overview of the tools and then leave the floor to Mauro in order to give you the second part related on the applications, okay? Let me give you also, because it will be relevant, especially for day 1 and day 2, a brief account of what we have done and what we have been doing in order to extend this multi-scale framework from atoms to the reactors to the level of structure-dependent microkinetic models. So by explicitly accounting for the structure of the catalyst as a function of the condition in the reactor given by fluid dynamics. We have done this. I don't want now to go into the details obviously for time reason. I just give it to you the relevant papers if you are interested. So we tackle this problem using both, thermodynamic methods that are going to give you the ground state shape of the catalyst. This is the first paper over here, basically coupling ab initio thermodynamics, Wolf construction, and microkinetic modeling. But also very recently, and this is this ACS catalysis I mentioned here, here you find the extension to the direct account of ensemble of shapes using a Boltzmann statistics in order to represent the possible occurrence of different metastables, particles that are representative of different minimum of the Gibbs free energy stability of the different shapes that you can get, for example, from an experiment, and to evaluate directly, thanks to the reactivity and the multiscale simulation, the effect of this structure directly at the level of, for example, reaction rates or convection in the reactor. The last paper that I want to point to you is this one, where we propose a parametrization of using extending DEP on the different phases of the nanoparticle. This is actually very useful because obviously if you are going to resolve at the level of the particle the different kinetics, well, you have also an explosion of complexity. So you don't have only to evaluate, for example, a nudge elastic band calculation to get an activation energy on one surface. You have to get it on different surfaces or even on steps or edges and so on, okay? Therefore, it's of utmost important to get a parametrization that allows you to skip some of these intensive calculations and to allow a parametrization of the activation energies, for example, of one facet on the basis of the limited number of information at the level of DFT nudge elastic band that you can get from the explicit calculation on other facets. But for time reason, I cannot now go into details of this. I just leave you as a reference. Right, to conclude what you have covered so far, so I hope to have convinced you that you need the reactor because if you think what you're doing in practice when, for example, you're measuring a rate, you never measure a rate per se. You measure something that happens in the reactor, and then later on, you interpret this as a function of the different phenomena that you have in the reactor. This, for example, happens when you try to perform a reactor in differential conditions in order to have, and to be able to extract directly the rate of the reaction, okay? You need to be sure that you are not affected by mass transfer, you have not make big mistakes in terms of approximation of the rates, so on and so forth, okay? On the other side, this observed functionality is clearly important when you think at the design of the reactor. If you go to industry, you need to design the reactor, now you have the material, now you want the material to perform well. So you need to identify operating condition that allows you to get the material to perform at best in your conditions. Means selectivity, means conversion, but means also stability. So avoid over temperatures, avoid the particular region where you have some pollutants. So then you have a lot of conditions. Name it will be relevant in any case, and they will be, described overall and will fall in this overall philosophy of the multiscale, representation of the reactor reaction event. If we concentrate on CFD, I show you how operator splitting, multi-region approaches, and CFD them. So starting from dynamic simulation, intraphase with CFD and fluidized bed reactor are very relevant. There are some other methods. We didn't have the time to cover today here. We have some, for example, linearization of a source term. If you are interested, just visit our website or get in touch with us. We were more than welcome to show you what we do. However, even if these are working properly, you are postponing somehow the difficulties in terms of computational time. So the chemistry is actually a bottleneck in your simulation. So you need to speed it up. I show you ISAT, I show you the cell agglomeration, and I show you the pre-computing of their activity as a sort of build-up of a sort of big data ensemble that you can interpret using machine learning, for example, and I show you this is so far a must for a first implementation of kMC in this kind of simulation. And then I show you also how hierarchical approaches can be a sort of enabling factor to reach and to bridge the gap towards real industrial situation or real stuff to be designed and done. And I also gave you a little bit of flavor of what we have been doing in the context of structure-dependent microkinetic model. Last, before stopping the first part, about tools. So far we have covered the theory. Now let me give you an overview of the tools, and then Mauro will basically build up from here by showing some details on some of these tools, and by giving you a direct applications of these tools. So theory, application, and tools. So at our GitHub website, you can get what we release as a freeware. So we have a version of the catalytic form that you can get from this GitHub link. I skip now the details. I think I've talked quite a lot about catalytic form in the last 2 hours. So you can see, you can retrieve everything from there, and Mauro will show you in practice how to do so. Also, some of the functionality in terms of structure-dependent microkinetic model can be get from this GitHub link, as well as the machine learning adaptive design procedure. So what I want to make as a point, and I know that Mauro will make this point as well. So for us, this machine learning is not only related to the CFD, but it's actually a very important point also to speed up classical reactor simulation with a great advantage. For example, if you think to control, okay, when you need a reactor response in a glimpse of an eye, and therefore you don't want on the other side to lose the fidelity and the accuracy of these multi-scale first principle tools. Therefore, machine learning is properly used can be quite an advantage also in that field. And as we'll show you later, we think that our developments can be quite important in this regard. Last point is more, if you want, an announcement rather than a real release, because at the moment we have an internal beta version that we are testing inside Polimi, and will be released shortly. Basically, it's a sort of reactor modeling suite, so macro scale, where we have all the different pseudo-homogeneous, heterogeneous model, intraphase phenomena, 1D, 2D models, as we derive, for example, in the last part of my talk. We intended this to be a sort of suite that covers all the macroscopic standard models that are used in the practical design of chemical reactor, and we expect this, for example, to be fully integrated to other softwares, for example, the one that were presented in the previous 2 days of the workshop, but will be more specific later, probably at the end of the summer, where will be released. So we'll find all the information on this GitHub or on our website or our socials. With this, I basically conclude with the acknowledgements. So first of all, I'm very thankful to the people that in the past, I would say 10 years, greatly contribute to the project of catalytic form that started with operator splitting, and now we ended up with the structure-dependent multi-scale modeling. In particular, I want to mention Mauro Bracconi, that will be also the speaker of the second part. The other students and PhD students that were involved in the project, in particular Giancarlo Gentile, Tiziano Maffei, Stefano Rebughini, and Riccardo Uglietti. I'm very thankful also to the different industries that basically supported this project all over the years, and in particular to the funding agency, in particular European Research Council with the ERC starting grant and with the React Pro project that is both are currently ongoing. I hope that this was an interesting first part. If you want, we have 10 minutes that we can use to handle some of the questions, and then 3:30 we are going to basically move to the break. We change the link and we move to the application part that will conclude the workshop. Okay, let's see. Just to pick some of the question, I'm asking now here the control room here in Polymere. So do you have any specific question that is actually interesting? So Mauro, you can, if you have already selected, tell me also which questions or publish so I can see it.
Okay, so basically the questions are not being published. So I think it's better to go through and answer to them one-to-one, or at least
okay.
some of them, and then we proceed with the feedback. So one of the questions we have is related to the situation where we have 5 or 4 different operations in the governing equations. So if we have simultaneously diffusive transport, convective transport, heat transfer, and then surface kinetics, and we lump everything in one single term in the governing equations.
Yes, we can. We do. So basically, we have our splitting is transport and reaction, which is actually the root of our problems. Basically, if you want, it is very much dependent on the difficulties that these additional operators are bringing to the system. So here, transport will lump together because basically they share the same difficulties, and consequently, you can handle it with the same strategies. But if you add something else, I don't know, could be, I don't know, radiation, for example, just to name a few, and this in principle, in some particular condition, they can include some particular feature of difficulties that can actually become limiting, then you have no limiting in the splitting of the operators.
Okay, so we have another interesting question, which is related to the different time scales which are present in a chemical reactor. So basically, how we can select the time step when we have very external fast mass transfer, or very slow heat transfer and moderate rate of the surface reaction. So is there one time step which control everything, or we can use different time steps for the different phenomena?
Okay, so basically, obviously, this falls in the category of the things that you have to check. So obviously, and this is a good, very good question, because make possible to highlight this point. What would be the time step splitting? How can we can know it in advance? You cannot. So you need to test. So typically, what we do some different runs by changing the time steps, splitting time step, and then we see at which point this the final solution is converged with respect to the time splitting. Okay. Obviously, you want to keep the time splitting higher if you can, because this allows you to go faster. Okay. But on the other side, you need to ensure that this time step is not going to interfere with the physics, because in the end, the phenomena are not splitted. They occur at the same time. So again, these are another way, and this I come back to one of my introductory slides, to the parameters that in the specific framework of the operator splitting must be checked. This actually is a very good question in this regard. What I can tell you in practice, that then you build up a sort of experience, and this is what we have done here, and then you know and how the system is behaving, how the algorithms behave, and then you can do some selected checks in order to make sure that you are treating the things properly.
Okay. Okay, so we have other questions which are related to the speed up techniques, and one is related to how often we update the cell beams distribution.
What is it? Beyond that, okay, I found it. In cell agglomeration is the distribution of cell. Okay, fine. Okay. This in the steady state simulation basically you know somehow how the system, what would be the initial and the final, the times, the variable span, okay? But obviously, this is something you need to check. Basically, you can say, okay, I know that in extreme case go to 0 to 1. Then I consider the tolerance given value, and then the number of beings that will be populated will be related to what happens in the simulation. So this is something that you can handle quite easily. Your question is actually relevant in the extension that we are now performing also in the dynamic extension of this cell agglomeration. What we do is typically at the moment taking the same approach. So you have some physical constraint, and we use this as a time span, and then you set a distribution, a sort of scale that allows you to categorize. Let's say, I mean, you can use a sort of schematic view of a scale of colors. These different scales is related to your choice of tolerances, so plus minus the variable that goes in that beans. The relevant check there, I would say, that is related to the fact that, again, you are converged with respect to your parameters in building up the beans. This actually, as I show you in the slides, if you have a very coarse, distribution of the beans, then you can be off, and therefore you have a trade-off between accuracy and computational time.
Okay. We have another question related to the ISAT technique, which asks if ISAT has different performances with different grid sizes. So if we change the mesh, how does this influences the affect the performances of ISAT?
This actually can be answered, in my opinion, in different ways. Let's say, first of all, you need to build up an history. So if you have a very complex mesh, you have a very hard time at the beginning, okay? Because you need to do all this integration for all over the mesh. Therefore, everything is related to the operator splitting and your handling of the ODE. I do not see now a direct, interference between the ISAT per se, so the build-up of the tree or the efficiently handling of the tree with the mesh. I would say that the most important point is related to this handling of the history of the simulation.
Okay, so I think we have 2 minutes more, so maybe we can have one last very quick question, which is related to how how the decision time is affected by the size of the kinetic scheme in machine learning techniques. How is the decision time of machine learning techniques affected by the complexity, the size and dimension of the kinetic scheme?
Well, obviously, as you know, machine learning works very well with a high dimensionality. So they're expected to behave very well as soon as you have a high number of points. The bottleneck that I try to highlight and I try to show, and is actually our specific contribution, I think, is mostly related to this, that if you have a situation where you have a lot of data to build up, then the training set is going to be really an enabling factor to make this possible from a practical point of view. So if I understand right the question, because I cannot read it right now, I would answer in this way.
I will add some detail during the part 2 on this specific aspect.
So with this, I think that we can conclude this first part. Now it's time of the break, where also you have to switch to the second link. As usual, I will send you an email right now in order to remind this, and so you have you can easily change from link number 1 to link number 2 of day 3, which is today. With this, I thank you for the attention, and I look forward to the second part and to the discussion at the end of this day. Thank you, and see you in 15 minutes in the second link. Okay, welcome back to the second part of day 3, and now I'm going to introduce Mauro Bracconi from Politecnico di Milano. Mauro, we are going to present this part 2 on the application of CFD and the coupling with kinetics. So Mauro, please, the stage is yours.
Thank you. So this afternoon we are going to cover the sort of technicalities and specific application of catalytic foam with some examples, along with the description and short tutorial of the usage of the adaptive design procedure for the machine learning technique. So let me start resuming with some background on catalytic foam. Catalytic foam is a numerical CFD code specifically conceived for the simulation of heterogeneous reacting flow. It uses the open foam framework as a pillar for the management of the equation discretization and for the usage of the finite volume method. Moreover, it is conceived in order to implement specific models in order to be able to account for the heterogeneous chemistry. And in particular, the catalytic smoke library enable us to deal with macrokinetic model, microkinetic model, and very recently we have also added the functionalities of dealing with kMC Monte Carlo methods. In order to carry out this kind of numerical simulation, we need some specific additional features which are provided by some external libraries, which are useful in order to make the solution of the stiff ODE solver. And then we can also use our in-house developed methodology in order to improve the computational burden, trying to reduce the overheads provided by the detailed accounting for the heterogeneous chemistry. So let's move to some more technical aspects. Catalytic foam is a numerical framework which is written in C++, and we have also some additional features, some external features such as the machine learning procedure, which now are written in the Python language. Catalytic foam is built upon the open foam framework and is currently fully compatible with the version 4x and 5x of open foam. We are currently planning to extend the compatibility to the newer version of open foam, but to this point, we provide a fully working version for these two open foam framework models. Catalytic foam, in order to properly work, requires some external library, and these external library are related to the management of the mathematical operation between vector and matrix, which is carried out by the quite famous Eigen library. And then we need the management of EXML file, which are the language in which the kinetic scheme are properly written. And we basically exploit the functionalities of the Rapid XML and of the Boost C++ library. Finally, we need another additional library, which is the OpenSmoke++ library, which is provided in a light version in the catalytic foam release, in order to properly manage the description of the transport properties, the calculation of the thermodynamic properties, and finally, to the evaluation of the actual reactor rates for the microkinetic models. Catalytic foam has been tested and is currently employed by a large number of different users under different Linux distros. So basically, we have a fully compatible version for Ubuntu, for CentOS, and for many other Linux distros. while the Windows compatibility is under assessment and development, and to this point we cannot provide a fully working version for the Windows OpenFOAM code. Finally, Catalytic Foam is a fully text-based software, which means that as Zacros, all the input files are text-based, and they are provided to the software without any kind of graphical user interface. Catalytic Foam is available online, so you can even now download the Catalytic Foam framework, which means the solver, the libraries, and the code from the Multiscale Catalysis Polimi GitHub repo, which contains all the other features we have developed in the Multiscale Catalysis group here in LCCP in Polimi. Once you have downloaded the GitHub repo by using the GitHub clone command, you have to enter, in order to install the Linux version of Catalytic Foam, in the Catalytic Foam directory. And once you are there, you have to do some preliminary stuff in order to properly create the correct installation environment. These steps are contained in the my-bash.rc file, and in the my-bash.rc file you have to specify 4 different values. The first one is the version of OpenFOAM you are going to employ between the 4x and the 5x. So if you actually want to use the 4x, you have to write minus the OF version equal to 40, or if you are using the 5x, the 50 value is the one which is for you. Then you have also to specify all the paths to the external compulsory libraries, like the Eigen, the Boost, and the Rapid XML, which has to be downloaded and properly installed and compiled on your machine in order to make Catalytic Foam available. Once you have modified this my-bash file, you have to save it and source it in a bash terminal. And at this point, you are fully ready in order to run the compilation of the software of our internal libraries in order to get the fully functionalities of Catalytic Foam. And to do so, you have just to type all wmake in your bash terminal. At the end of the installation, you will have on your desktop, laptop, or even on your high-performance computer system the possibility of carried out heterogeneous chemistry simulations in complex three-dimensional geometry, coupling the detailed description of the heterogeneous chemistry with the computational fluid dynamics. In particular, Catalytic Foam, as Matteo told before, is able to manage many types of different reaction rates. So first of all, we can deal with macroscopic reaction rate, like the Langmuir-Hinshelwood model, which Dion Vlachos explained in day 1. We have also a fully compatible version of a microkinetic engine, so we can easily incorporate in our simulation the microkinetic scheme, which has been in day 1 too. And finally, we have the features and the functionalities in order to be able to couple the kinetic Monte Carlo simulation within the reactor models by using specific techniques. The kinetic Monte Carlo was the object of the workshop provided by Michael Stamatakis in day 2. On top of this, we provide also some specific speed-up techniques in order to make the simulation, in order to reduce the computational cost of the simulation and to make the simulation feasible. In doing so, we can use the pseudo-adaptive population, we can use the cell agglomeration, and we can also employ machine learning techniques in order to cut down the computational burden. We now briefly see how to include the different types of heterogeneous chemistry models within the CFD simulation in the context of the Catalytic Foam framework. So the most simple rates we can deal with are the macroscopic reaction rates, the one which are already provided in a specific form which accounts for some specific hypothesis on the mechanism behavior. So maybe we can have some specific RDS or some other specific hypothesis which produces a specific macroscopic reaction rate. This kind of system can be directly introduced in the open form and in the catalytic form framework by using a specific functionalities which is inside the catalytic form code. So basically, this kind of system has to be directly hard-coded in the main framework of catalytic form by modifying this reaction rate file, which is provided in the solver directory. Following the structure of this example, you have to provide all the specific information that you need in order to compute your reaction rate. And on top of this, you have also to generate a very simple dummy kinetic scheme in the kMC format in order to enable us, our library, to properly compute the transport and thermodynamic properties based on that database. Some examples are already available or will be very soon provided in the GitHub file in order to show you in specific tutorials how to create this macroscopic reaction rate model for the open form framework. A different story is, has to be considered if we have to deal with microkinetic models. So every time we need to work with microkinetic models, we need to set up a binary format of the kinetic model itself, which can be processed by the catalytic form framework in order to compute the reaction rate of each of the elementary steps, and then to combine those values into the net production rates of all the species. To achieve this, we need to properly define the kinetic scheme, and we have also to provide thermodynamic and transport database, which can provide all the features and all the information that we need to a specific kinetic preprocessor in order to build up the final kinetic model, the preprocessed kinetic model in the binary format. So what does it mean to create these three bench of files? Okay, so first of all, we need to create 4 different files, and we need to, which can also be already available in online. So there are some databases where you can find examples of these kinetic scheme files. But anyway, what we have to create is a kinetic file for the homogeneous portion of the reactions, where we are going to define the number of species, the stoichiometry, and the specific kinetic parameters of every homogeneous reaction. Then we have to provide another file, which is a surface file, which do exactly the same of the kinetic file, but in this case for the surface chemistry. So we have to provide all the surface species, all the adsorbed species, and then we have to consider all the different kinetic parameters and type of reaction which can eventually occur on the catalytic surface. Then we need to consider 2 different databases. The first one is a thermodynamic database, which provides information in order to compute specific heat capacities, enthalpies, entropies, Gibbs free energy. So all the information that can be important to be computed in order to evaluate the kinetic scheme and the reaction rate. Finally, since we are dealing with a macroscopic and detailed description of our reactor, we have also to compute the transport properties of the species. And this means the diffusivity, the viscosity, the thermal conductivity, in order to properly introduce this quantity in the governing equation in order to reach a proper description of the macroscopic behavior at the macro scale. And to do so, we need a specific database which contains the information which are required in order to compute these transport properties by means of the kinetic preprocessor. So let's have a brief look on how does this file look like. So basically, according to the kMC format, the homogeneous chemistry file consists of different sections, and these sections are related mainly to the description of which are the elements which are present inside our kinetic scheme. Then we have to specify which are the species which are involved in the chemistry, both heterogeneous and homogeneous chemistry. And then we finally have to specify, according to the chemking format, we can specify according to the different chemking formats, several types of homogeneous reactions, which can either be equilibrium, just forward reaction, they can involve a third body, and many other options in order to properly account for the homogeneous chemistry. Then, in this reaction subfile, we have also to introduce the kinetic parameters we have to employ in order to compute the kinetic constant, which can be then employed in order to evaluate the specific rates. And the kinetic parameters are evaluated according to a modified Arrhenius equation, which consists of a pre-exponential factor A, which is the first term here in this set of data. Then we have the exponent of the temperature dependence, and then finally we have to report the activation energy of the specific step. The structure of the file for the heterogeneous chemistry is really similar. First of all, we have to specify which is the type of the active site, so we can specify a specific material as an active site. Then we have to clearly identify which is the site density in order to enable the code to compute the kinetic constant. And then we have to report which are the adsorbent species on the catalytic surface, which are the ones which are involved in the microkinetic mean field chemistry. Then we have once again to specify all the reactions, and this reaction has to be specified according to a sequence of direct and reverse, forward and reverse reaction of each type which are involved inside the system. So for instance, here you can see the hydrogen dissociative adsorption over rhodium. So basically we have to specify first the forward reaction, the adsorption of hydrogen, and then we have to follow this reaction with its reverse, which is the desorption of hydrogen from the surface. Building all this reaction together makes the capability to the system to properly compute the kinetic rate and then the net production rate inside the system. Okay, moving to the thermodynamic properties, the file follows this specific structure for each species that you are considering. You have to specify their name, and then you have to specify the atomic, the elementary composition, the atomic composition, so how many atoms of each species are present. Then you have to identify which are the ranges for the temperature. So within which boundaries we can compute the thermodynamic properties of this specific species, in this case between 300 and 5,000, with a transition between different set of coefficients at 1,000. And then we have to report the set of the NASA coefficient for the evaluation of the specific heat. And in particular, we have to report two different sets of coefficients. The first one related to the low temperature, the one between the minimum and the transition temperature, and then the second set related to the higher temperature window, which is the one between the transition temperature and the maximum temperature inside the system. On the basis of this coefficient, according to the formula that we have reported here in this box, the numerical code is able to compute the CP, the enthalpy and the entropy and so on and so forth for all the species. And then it's able to properly combine according to a specific thermodynamic model to compute the mixture properties. For what concerns the transport properties, in a microkinetic model, you have to specify once again the name of the species and some other specific information which has to be reported in order to enable the system to compute according to specific formulas all the transport properties for the specific species, and then according to the combination rule, the transport properties inside the mixture. Once you have this system properly set up, you are now in the capability of creating the preprocessed kinetic scheme by calling our kinetic preprocessor with the specific input which are provided by the thermodynamic database, the transport database, the homogeneous chemistry scheme, and the surface chemistry scheme, in order to provide an output folder, which is in this case is called kinetics, which enable us to carry out the CFD simulation. Finally, the third option that we have in order to carry out this kind of simulation is to employ kinetic Monte Carlo schemes. The usage of kinetic Monte Carlo schemes is achieved, as Matteo Maestri explained before, by exploiting an effective decoupling between the scale. And in doing so, it's possible to pre-compute the computationally expensive kinetic models, tabulate this value by means of specific techniques such as the machine learning ones, and then introduce the pre-computed chemistry, which can be computed very efficiently in a very low amount of time inside complex geometry such as the one of an open cell forms as reported in this simple example. Okay, so now we have an overview of what we can pass to catalytic foam in order to carry out specific computational dynamic simulation of heterogeneous chemistry reactors. But how does the solver work? So basically, the solver exploits, as Matteo Maestri explained today, the operator splitting approach. And in doing this, we can briefly outline this flow chart of the solver operations. So let's go through this flow chart just to have a clear idea, a clear picture of how does catalytic foam works. So first of all, at the beginning of the time step, we are here, and we need to make all the calculation in order to being able to move to the following time step. So first of all, we have to compute the delta t, which means the time step integration time, and this is carried out by using the in-house features of OpenFOAM, which enable us to adopt an adaptive time step in order to respect a specific current value in order to be compliant with the CFL requirements for the time step in transiency and the CFD simulation. Once we did that, we compute all the properties that we need in order to make our calculations, transport properties, thermodynamic properties, what we need in order to solve the predictor in the operator splitting approach, which is, according to our algorithm, the solution of the transport properties. So in this step, we are going to solve according to a segregated approach in a sequential manner. First of all the gas species, the transport of the gas species in terms of their material balances, followed by an energy balance, which enable us, in case of non-isothermal simulation, to follow the temperature evolution inside the system. The solution of the transport properties is the initial condition for the corrector of the operator splitting approach, which is represented by the solution of the chemistry, of the solution of all those batch reactors which correspond to each computational cell in our computational domain. At this point, we have increased, we have proceeded in the time evolution of our system for the species balance and for the energy balance by also accounting for the reactions by means of our catalytic foam features, and we just now need to solve the Navier-Stokes equation in order to update the flow field, which means the velocity and the pressure fields inside our simulation. And this can be done by using the piezo or pinball features, which are provided by the OpenFOAM framework. At the end of the time step, we have just to increment the time step and restart from the beginning of this simple flow chart. The simulation ends when we achieved the computational, when we achieve the final time we have defined as the one we would like to employ for our calculations. Catalytic foam enables us also to follow the evolution of the system, so we can save many snapshots of what happens during the evolution of the system in case we are interested in the transient and dynamic behavior of our reactor, or we can just skip to the final steady state solution by giving a sufficient time to achieve the steady state to the dynamic simulation. The main features of this system is that, according to its structure, we are not any kind of limit in the number of species and reactions we can account for. And in my view, more importantly, we have also no limit in the geometry. So we can try many different reactor geometries. We can have an efficient screening of the performances of innovative and new technologies by using this kind of tools in order to understand their performances in the context, for instance, of process intensification or reactor design and reactor analysis. Okay, so at this point, we have had an overview of the concept and the capabilities of catalytic foam. And now it's time to go deeper in the overview of the code by going into the description of a simulation folder. So what you have to create in order to run your first catalytic foam simulation. Catalytic foam is based on the open foam environment. So he employs the same folder structure as a conventional open foam system. So if you are familiar in any way with the open foam environment, you can easily understand how to set up a catalytic foam simulation. In the case this is your first CFD approach, the text-based catalytic foam input file are still very simple to be understood, created, and then submitted for the solution through the software. So basically, the folder structure consists at least of these three important subfolders, which are the zero folder, which we will see in a while its purposes, but I can briefly anticipate that it contains boundary and initial conditions. The constant folder, which contain all the information related to the computational domain and the physical model we are going to employ for the solution of our system. And then the system folder, which is the control room of your simulation. Here, in this folder, in the system folder, you can find all the information related to discretizations, numerical methods, control of your simulation in terms of time step, snapshot saved, and also you can have all the detail in order to build your own mesh and to exploit the open foam features for the parallelization in the context of APC system. Okay, let's start with the constant folder and to have a look on what is inside and what is the specific features and purposes of each of these files. So the constant folder, as I have just said, it's the source of the information for the catalytic foam in the context of the computational domain, and the computational domain is contained in this polymesh folder, which can be generated, and we will see later on with different software and techniques. The polymesh folder contains some files which are the information to the solver of the actual geometry you are going to solve. So in these boundary faces, neighbor, owner, and points, you have all the position of your computational cells, the interconnection between the cells, which are the boundary, which are the external surfaces of your cell in a non-humanable readable structure, but in a very efficient and computationally performant way for the numerical simulation of the system. Then, in this folder, we have also the information related to the physical model we are going to solve. And in particular, in the solver option file, you have available all the specific features. You have available the selection of all the specific features we can employ in a catalytic foam simulation. We can briefly go through this file, but I will focus later on during the preparation of a specific case study on the purposes of each of this entry. But basically, in the solver option file, we have the information related to the pre-processed kinetics. So basically, here we tell to the catalytic foam solver where we can actually find our pre-processed kinetic model. And then we specify in the physical model all the information related to the specific operator splitting algorithm we would like to employ, if we would like to switch on or switch off chemistries, how much catalyst is loaded inside the system, and many other specific information. In the same file, we have also the control of the numerical solver, which are in charge of the treatment of the homogeneous and the heterogeneous chemistry. So basically, every time we have to account for the presence of the chemistry inside the system, we have to solve an ODE system. And this means that we have to provide specific ODE solver, which are conceived in order to treat with the strong nonlinearity and high stiffness of the chemistry problem. Here, you can specify which solver you would like to employ. In the GitHub version of the catalytic foam, just the OpenSmoke in-house solver is available. Then you can specify the various tolerances along with the maximum order of the solution. The OpenSmoke ODE solver is specifically conceived for stiff system and is extremely efficient for the solution of the heterogeneous and homogeneous chemistry. In this folder, you also find the information and all the features for the tuning of the ISAT algorithm that Matteo Maestri this morning explained. So basically, the concept behind the algorithm has been seen before. Now, here, with this input file, you can tune the tolerances, for instance, or you can tune the size of the different lists and binary trees which are employed in order to properly tabulate and store the information generated on the fly. Sorry. Okay, and in the same file, you have also the information related to the tuning parameters for specific features that are provided in the ISAT algorithm for heterogeneous chemistry we have implemented some years ago. Okay, we had an overview of the constant folder except from this G file, and this G file is related to the definition of the direction of the gravitational acceleration inside the simulation, which can be very important in the case of system where buoyancy is a very relevant feature. If we move to the analysis of the system folder, the system folder contains all the simulation control. I'd like to say that this system folder is the control room of our simulation. Here we can really play with all the numerics behind the CFD in order to achieve a correct discretization and a correct spatial and temporal discretization of our solution. So basically, we can consider first of all that we need to generate the discretization, and in order to generate the discretization, we have to create the mesh. And the most simple way to create the mesh in OpenFOAM is through the block mesh utility. And in the system folder, you can find the block mesh dict file, which contain the information related on the generation of the computational mesh. Today, due to the sake of time, we are not going through how to create the mesh with block mesh, neither with other specific tool, but you can find the already prepared block mesh file on the GitHub example, and you can also find some additional information in our website. Okay. Moreover, the other information which are present in this system are specifically determined in order to define how often we would like to simulate the system in terms of snapshot, in terms of time step, in terms of maximum current number, and to do so, we need to play and tune the entries of the control dict file. In the control dict file, we can specify which is the start time of the simulation, which is the end time of the simulation, how often we would like to write on file our solution by using the write interval entry, and then we can also play with the write format. We can use the ASCII or binary in order to save computational space. We can also define, and this is one of the most important elements in a CFD simulation, the maximum current number. The value of the current number is really relevant for the control of the stability of our simulation. And in case of a heterogeneous chemistry coupled with CFD simulation, the maximum current number that we can manage is unfortunately much lower than the conventional one of cold flow simulation. We usually suggest to employ maximum current number between 0.05 and between 0.01, which are dramatically lower than the conventional one for cold flow simulation, which are in the order of 0.7, 0.8. In the same folder, we have also the information and control about the decomposition of the computational domain. When we have to simulate very big systems, like the cylinder packet bed Matteo Maestri showed today, your laptop is not enough in order to carry out such kind of large-scale system. So basically, in order to make the simulation feasible, what we can do is we can exploit the domain decomposition and parallelization of the solution, which is the idea behind this. In principle, we can say that if we have many CPU, 10, 20, 100, 1000, according to your specific computational power, you can split and subdivide your computational domain in order to assign just a portion of the entire system to a specific CPUs, keeping just one of the CPU in order to managing and controlling the solution of each of the workers. In doing this, we are in some way reducing the amount of the computational effort of each specific CPU, and in doing this, we can achieve a relevant speed up of our simulation. In the decomposed per dict system and file, you have the various possible way of decompose the computational domain and the total control of the number and order of the composition of your system. Finally, in this folder, you have also the control on the temporal and spatial discretization scheme that you are going to employ for the solution of your equation. So when you generate the computational domain, you are going to introduce a geometrical discretization of your problem by splitting it in a certain amount of computational cells. Then, when you have to transform your governing equation from their balance formulation to a numerical system which can be actually solved, you have to introduce what is usually called as discretization system. So basically, if you consider, for instance, a simple finite difference method, you have to define if you would like to have a forward or backward discretization of your first and second derivative. Along the same line, in finite volume method, you can use specific discretization schemes, and OpenFOAM has plenty of options of different discretization schemes, both of first and second order, and you can also eventually employ third and higher order schemes for the solution, for the discretization of the divergence term, which are the convective term, for the discretization of the gradients, and also for the discretization of the diffusive term, which are represented by the Laplacian scheme. Moreover, the temporal integration of your system can be controlled by using different techniques, which can be a Euler forward method, an Euler backward method, or a Crank-Nicolson method in order to try to improve the temporal accuracy of your simulation. Okay, finally, in this folder,
we have the last dictionary, which define now the numerical solver for the discretized governing equation. So we start from the balance equation, we get a discretized version of the balance equation. Now we need something which enables us to solve this equation in order to get the new value of the specific variables that are involved in the solution of the problem. And to do this, we have plenty of different numerical solvers, which are provided by the OpenFOAM framework, which we can fully exploit inside our numerical simulations. For instance, we can use preconditioned conjugate gradient method. We can use GAMG methods. We can specifically tune the numerical solver in order to the one that best suits the numerical requirements of our specific system. Okay, we have seen now the constant and the system folder, which are the one which control the physics and the solution of our system. Now we need to understand the core of our input file, and the core of our input file are the initial and boundary conditions. Since every time you need to solve a chemical reactor, what in principle you have to do is to understand which is the transient or steady state behavior according to a specific input information inside your domain, which means that you have to properly specify both the initial conditions, and the initial condition refer to what is at the initial stage of your simulation. So at time 0, what the system sees when you switch on the solver, and the boundary conditions, which are the information which provided through the external boundaries of our domain in order to simulate the physical behavior of our specific system. In every catalytic foam simulation, what we have to provide are some specific files which correspond to the variables which have to be solved. And in particular, the compulsory value and files that have to be considered are the files for the reactants, which means all the species that are involved in the kinetic mechanism should be introduced inside the 0 folder as a specific file. In this case, we have a kinetic scheme, a simple and trivial kinetic scheme which involves methane, oxygen, and nitrogen. And so in my 0 folder, I have a value, a specific file for methane, a specific file for oxygen, and a specific file for nitrogen. Then each of these files contains the following structure: is a dictionary too, and first of all, the first entry is related to the internal field, which means to the initial condition. So this value tells to catalytic foam which is the value of methane at the beginning of the simulation. And then you have the information related to the boundary conditions which are required in order to properly solve the degree of freedom for the solution of the numerical equations. We can go briefly through some type of these boundary conditions, but I would like emphasizing that we have developed in our work a specific boundary condition which is named catalytic wall, which is specifically conceived for the treatment and the management of the heterogeneous chemistry in CFD simulations. In the boundaries where you don't have the heterogeneous chemistry, then you need to specify accordingly to the physical behavior of the specific portion of your computational domain the corresponding boundary conditions. So for instance, this other boundary, which is named inert wall, is an inert solid surface in my reactor, and I can basically employ a Neumann boundary condition for this variable, which employ zero consumption or production of this species on that surface. And then I have to specify, obviously, the Dirichlet boundary conditions for the inlet value, which means for the region of our computational domain where the species enters inside the system. And then we can employ the corresponding boundary condition for the outlet of the domain by choosing the proper one according to the many present in the open foam environment. In this case, since this simple case study reaches a stable solution at the outlet, so no more variation are present at the outlet of our reactor, we can consider a boundary condition for fully developed flow, which correspond to a Neumann boundary condition at the reactor outlet. The same structure has to be reported for all the species inside the kinetic scheme, by keeping in mind that catalytic foam work by employing mass fractions. So all the governing equations are written on a mass-based formulations, and so all the information related to the initial conditions and to the boundary conditions has to be reported in terms of mass fraction. So in this case, for methane, we are supplying to the system a stream which contained 17% on a mass base of methane. By moving to the other important quantity for the solution of the heterogeneous chemistry, we have to consider the temperature. Once again, even for this variable, we have to specify, first of all, the internal field, so which is the temperature in Kelvin, which is present inside the system at the beginning of the simulation, and then we can specify the corresponding boundary conditions by keeping in mind that the boundary condition where the heterogeneous chemistry occurs has to be defined as a catalytic wall boundary conditions. Then, since we are solving a Navier-Stokes equation, we have to consider both the velocity and the pressure as two specific variables, independent variables that has to be solved in our system. So this means that we need to provide initial conditions for the velocity and also boundary condition for this quantity. I would like to stress that since the velocity is a vectorial field, you have three components of the velocity. You have to specify the internal conditions and the boundary condition of the velocity by considering both these three directions of space. So this is the contribution of the velocity in the x direction, this one in the y direction, and this one in the z direction, according to the specific reference you have employed for the generation of your computational domain. The boundary conditions for the velocity are quite different from the one we employ for temperature and species, since we have to consider just the corresponding behavior that the velocity field has on solid surfaces and at the outlet of our domain. Once you have solid surfaces, you have to consider a no-slip boundary condition, so your fluid is not moving on whatever solid surface you have inside your system, either inert, either catalytic. And at the outlet, you can choose a specific boundary conditions according to your specific problem. In this case, we decided to set the inlet velocity at the beginning as a flow rate of 1 meter per second in the x direction, but this is just one possibility according to the geometry of this simple test. For what concerns the pressure, we have the same structure. We have to define the internal conditions in terms of the initial conditions, in terms of pressure in Pascal. And then we have to define the boundary conditions by keeping in mind that for the solution of the Navier-Stokes equation, we have to define the pressure where we are not imposing a Dirichlet boundary conditions for the velocity. So if you remember, just some seconds ago, I've shown you the velocity boundary condition. And the velocity boundary condition has a fixed value, a Dirichlet boundary condition at the inlet. And as you can clearly see, in this system, we are going to specify the pressure not at the inlet, but at the outlet, where we don't have a specific value for the velocity. Okay, we have seen the pressure the pressure file and also the zero folder, now we can move on what is the output of a catalytic foam simulation. So let's imagine that, let me say that we have run the simulation. We will see later how to do it. We have run the simulation. At the end of our simulation, we will find in our folder, the one which at the beginning contains just the zero, the constant, and the system folder, these additional time folders, which represent the snapshot of the solution of our reactor saved with a certain frequency given by the control dict entry write interval. Each of these subfolder will contain all the variables that has to be solved for the solution of our system. So if we start that simulation of methane and oxygen, which means methane combustion in our reactor, and we let it run, according to a specific microkinetic model, we can have several species present in the gas phase. Here you can see that you can have methane, methyl radical, CO2, CO, and many other species. But you will also have all the information related to the surface species and on the adsorbed species. So you can clearly identify that we have adsorbed CO2, adsorbed water, the rhodium-free site, since this is a kinetic scheme which considers rhodium as the active phase. So basically, within each of these folders, you have the entire set of spatially resolved solution of your computational domain. And this can be easily processed in order to have a visual overview of your results by using the Parafoam tool, which is an OpenFOAM provided plugin for ParaView, which enable you to properly understand and go in the detail of the flow field and mass and temperature profile within your reactor. Moreover, OpenFOAM and catalytic foam give also the possibility of export the solution as a VTK format, and the VTK file are very easy to be post-processed by means, for instance, of Python C++ script, enabling you in the routinely analysis of your results without the necessity of looking into them by a visual inspection into the detail, into the results, but by using quantitative calculation provided by specific script and tool. Okay, so at this point, we have had an overview of catalytic foam structure and functionalities. So now we can move to the analysis of a simple case study. So Matteo this morning showed you a very simple case of a string reactor filled with some Raschig rings. Now we will try to do something which is similar to this by considering a string reactor too, but where we have loaded 4 spheres. And this case study is also available and on the GitHub repository already configured in order to be perfectly run with the catalytic foam solver. So let's consider what we would like to simulate. In this picture, we have a sketch of the geometry we would like to investigate. So we have this rectangular box, which is our reactor tube. So basically, this is where the fluid flow will pass through. And then we have 4 spheres perfectly aligned within this reactor box, reactor tube. The pellets have a diameter of 4 millimeters. We consider an isothermal simulation of water gas shift on a rhodium catalyst by considering an equimolecular feed of CO and water with a CO mass fraction equal to 2% and with nitrogen as inert. We are also considering a low flow rate in order to keep the system in laminar conditions, which is equal to 2.4 normal milliliter per second. The kinetic model for this water gas shift on rhodium is an UBI microkinetic model derived for the C1 activation on the rhodium catalyst. It consists of 16 gas species, 11 absorbed species, and as a whole of 80 elementary steps. So this means that our kinetic model is consists of a certain amount of species and steps that has to be simultaneously accounted in order to solve our system. Okay, this picture is a sketch of what we would like to solve, but this cannot be employed for the solution of our system, since the solution of our system goes through a discretization of the geometry in a computational mesh. So the first step of every catalytic foam simulation, but I would say of every CFD simulation, is the generation of the computational domain starting from our geometry, our idea, our system that has to be investigated. To do this, we can employ several tools which are available both in OpenFOAM, such as the block mesh and SnapPX mesh mesher present in the OpenFOAM framework, but we can also fully exploit many commercial software like Quantwise or ANSYS Fluent or Gambit or many others, which can be easily imported in the OpenFOAM framework by specific tools that are present there. The discretization of our computational domain is the most important part of the solution of our system. If we are going to employ the wrong discretization, which can be too coarse or which cannot capture the important detail of our computational domain, our final result will be garbage. So even if we have a perfect, a wonderful solver, even if we have the best microkinetic model that we can conceive, if we are going to provide to the system a bad computational domain, a bad description of the specific features of our system, the results that we will have will not be meaningful, will not reproduce the physically sound behavior of our system. So who holds the mesh holds the solution of our system. And we will see in a while how we can be sure that we achieve a mesh independent result along with a relevant description of the important features in our computational domain. But before doing that, let's see how to set up the case and which are the results for a specific discretization and solution of our computational domain. So we have generated the mesh by using, in this specific case, block mesh first, and SnapPX mesh have the final tool in order to fully resolve the geometrical features of our spheres. Once we have this mesh, what we have to do is to set up the simulation according to the behavior and to the specific system that we have in mind. So basically, the first step is to assign to each of the boundary a specific name in order to enable then the actual definition of the boundary conditions. So in this system, I have generated the computational domain in order to have an inlet phase, which is here hidden by the first sphere, where the gas will stream through. So this is the region where my fluid will enter inside my computational domain. Then I will have an outlet phase, which is which conversely is the region where the gas will leave my computational domain, where my fluid will leave my domain. Then I will have the surrounding box walls, which represent my reactor tube. And so I name them inner wall in order to remember me that they are not reacting, they are not catalytically activated, they are just solid surface which steer the fluid to stream through this specific reactor. And finally, I have the external surfaces of my catalytic sphere, of my catalytic pellet, which has been named reacting wall in order to resemble the fact that they are be responsible for the reactivity for the heterogeneous chemistry inside this system. Once I have defined the name of the patches, I have to specify the boundary conditions and the initial conditions in order to then fill the text-based input file of the catalytic foam framework. So first of all, let us focus on the initial conditions. The initial conditions tell us how is the system at the beginning of our simulation. So in this simple case, we decided to start from a condition where we have a uniform fluid flow inside our domain equal to 0.5 meters per second in the Z direction, which is this longitudinal direction in the reactor. An outlet pressure of 1 atmosphere, which means that we are discharging our gas to the atmosphere, an inlet temperature and a homogeneous temperature in our system of 850 Kelvin, and then a uniform composition in our system corresponding to the 2% of CO, 2% of hydrogen, of water, sorry, and 96% of nitrogen inside the system. I define these initial conditions since I'm just interested to the steady state behavior of my reactor. But in case I would be interested in the dynamic and transient behavior, I would eventually impose specific initial conditions in order to understand which is the evolution of my system close to the starting point, close to a specific starting point. So this is up to you and to your specific requirements in your specific simulation in order to properly follow what is the physical behavior that you need to investigate with this system. Then we move to the description of the boundary conditions. And the boundary conditions require to emphasize and describe the importance of the physics and how the physics has to be reproduced inside the system. So for instance, for this specific case study, we would like to introduce our gas with a flow rate of 0.5 meters per second. We are going to introduce the same composition of the species, and then we are going to consider the system isothermal, which means with a constant temperature, and we are going to employ a zero gradient boundary condition for pressure, since at the inlet phase we have fixed the velocity. I remember you that where we fix the velocity, we cannot fix the pressure too. Moving to the inert wall, we have to reproduce the behavior of a solid surface, which see a gas streaming close to it. So this means that we have to employ a no-slip boundary condition, telling that the system is, the fluid is not moving on the catalytic, on the solid surface. And then we're going to employ zero gradient Neumann boundary condition for all the species in order to avoid any heat transfer. Since we have zero gradient of the temperature, we are considering the system without any kind of heat losses through these boundaries. We have zero gradient of pressure. We have defined the velocity, so we cannot define the pressure too. And then we have zero gradient for the mass fractions for the gas species, since we don't have any kind of production or consumption of the species on this solid wall. At the outlet, we have a different behavior, which correspond to fully developed flow for the velocity, the species, and for the temperature. So we are going to employ zero gradient for all this quantity, since we are sufficiently far away from the last sphere in order to have already a well-developed flow. And then we are going to impose the pressure at the outlet. Finally, on the reacting wall, which is the core of our catalytic simulation, we are going to employ a no-slip boundary condition. A catalyst is still a solid surface where the gas is not moving. We are going to employ zero gradient for the pressure. We have fixed the velocity. And then we are going to employ zero gradient of temperature, since our simulation is isothermal. And finally, we are going to employ the specific boundary condition we developed for the treatment of the heterogeneous chemistry. So now that we have properly set all the boundary conditions in our system, we need to translate those boundary initial conditions in the catalytic foam input file according to the structure we have seen before. So basically, for instance, for pressure, we are going to introduce the value of the internal field, the value of the outlet, and then the specific boundary for the other phases. And the same for one of the reactants. Here I have reported the water input file, which has an internal field of 2%, an inlet composition of 2%, and then zero gradient and catalytic wall on the reacting surface. Then we need to specify which are the physical models we would like to employ in our system. So first of all, we need to define the kinetic scheme. So here we are going to define that, okay, we need to employ the VGS UBA kinetic scheme properly pre-processed, which contain the 16 gas species, the 11 absorbed species, and all the elementary steps we need for the solution of the system. And this is the actual path. So basically, this VGS underscore UBI folder is located inside the simulation folder. And then in that folder, you have the kinetics pre-processed code, which is in the subfolder. Then you have to specify which is the inert species. Since the system is going to solve all the species except to the inert one, and is going to employ the inert one to close the stoichiometric relation. And then you can move to the definition of the physical model. So basically, first of all, you can decide which kind of operator splitting algorithm you would like to use. Here in this simulation, and we suggest to employ for your simulation the transport reaction momentum splitting rule, which is the one corresponding to the flow chart I have shown before. But you can try to play with the other transport rules, with the other policies that we have, which maybe are more specifically functional for your specific case. Then you can switch on and switch off the chemistry. In this case, we are just interested in the heterogeneous chemistry. So basically, we switch off the homogeneous reactions and we consider just the heterogeneous chemistry. Then we need to specify the catalytic load. And the catalytic load is a very important information which tells to the system which is the actual catalytic surface with respect to the geometrical surface. So basically, what you have in the reality is that your catalytic pellet or your washcloth or whatever will not be perfectly smooth, and its surface will be exactly equal to the geometrical one. But you will have, and you want that those features will be present. You have pores, you have roughness, which increases the actual surface area available for your catalytic surface. So with this specific feature, we are going to tune the geometrical surface in order to properly account for the actual surface of your catalyst, and consequently, in order to properly describe the actual amount of catalyst that is present in your system. Then you have to specify which is the name of the catalytic boundaries by filling this list here. In this case, we have just one boundary, which is the reacting wall, and so we can just introduce one entry. Then we have to decide what we would like to do with the energy equation, and specifically in this case, we would like to run an isothermal simulation, which means that we can switch off the energy equation. Then we have other specific features which can introduce different physical models. So basically, the mass diffusion in energy equation tell to the system, and if in the energy equation you would like also to account for the contribution related to the mass diffusive terms in the enthalpy transport. In this case, since the energy equation is off, this is ineffective. Then you can also consider the effect of the dP/dt term in the energy balance, but once again, since the energy balance is off, this term is ineffective. And then finally, you can consider also the Sorey effect in order to account for the temperature-driven mass diffusion. Finally, you can also specify two different models in order to describe the diffusivity inside the system, but we are working on an additional one which will be made available quite soon on the GitHub repo. The current model available are a thick multi-component diffusion, which is the one which is set in this case. So multi-component is related to a multi-component thick diffusion. Or you can also employ Lewis number in order to compute the diffusivities. We are working and we are planning to introduce also a Stefan Maxwell description of the diffusive terms quite soon. Okay, now that we have set up our case study, we are ready for our simulation. So basically, in that folder, you can just open a bash terminal and you can run the catalytic pimple foam code, which after a while will provide you the numerical results in the text format I've shown you before. If you employ at this point the ParaView software, you can visualize the numerical results you have achieved. So for instance, here in this left box, I'm going to show you the velocity streamline in this specific system. So you can clearly see where you have the acceleration of the fluid, which occurs here in this region, since the other portion of the sphere are quasi in contact with the wall. So the open area, the cross-sectional area which is available for the fluid to stream through the structure is reduced, and to the continuity equation we have to increase the velocity in order to guarantee the conservation of the total flow rate. But then you have a decrement of the velocity in this region where you have a larger area, and so on and so forth. It's hard to see, but in this outlet region behind the last sphere, you can also see the presence of two counterclockwise vertices, which are correctly reproducing the fluid dynamic behavior of the system at this Reynolds number. At the same time, we can also visualize slice. So in principle, in this picture, I'm going to show you a slice which is cut here in the half of our domain, which reproduces the pressure distribution in our system. Differently from macroscopic reactor model, in CFD, you have the actual resolution of the pressure to the cell, to each different cell. So you can consider the aspect of different pressure conditions in each point of your catalytic reactor. Moving to more chemical relevant information, the output of the simulation are also in terms of coverages of the surface species. So here in this top left box, in top left picture, we have the hydrogen coverage on the system, and we can clearly see that the different environment which is close to the catalytic surface in different position in our system determine the presence of different composition of the coverage species along the surface. As a consequence, the net production rate of CO2, for instance, is changing not just along the reactor, as could be forecast by macroscopic reactor models, but also radially along the catalytic pellet due to the different distribution of the mass and pressure field close to the environment. This is a very simple example of the description of the system in terms of productivity. I have shown you also some other case study with cylinders, as Matteo already shown, but we can also have run simulations for open cell foams with different distribution of temperature and species also inside the structure by fully exploiting the multi-region approach. An important point in this kind of simulation is the adoption of a correct meshing strategy, and adoption of a correct meshing strategy is pivotal, and in these terms we need to employ different grading close to the surface and carry out a mesh convergence analysis in order to get mesh independent results. Okay, if we now move to the tabulation of models with machine learning, we can briefly see how we can employ the adaptive design procedure. So the concept behind this system is the employment of machine learning methodology in order to tabulate complex and large kinetic model. And to do so, we employ a specific design procedure for the computation, for the training point. The procedure is available on GitHub. You can download and you can try to play with it. I can show you some specific features very, very briefly. So basically, the adaptive design procedure works in this way. We have a function that has to be approximated, and this function deal and talk with the adaptive design procedure with efficiently define the position where this function has to be computed in order to provide an accurate surrogate model via machine learning. If we move to the analysis of, for instance, microkinetic or kMC simulations, we can substitute this general objective function with the specific net reaction rates, which can be given by kMC simulation or microkinetic models. So the adaptive design procedure talk with these specific reaction rates and kinetic models. This determines the position of the simulation of the microkinetic or kMC model and create the surrogate model, which can be then implemented in CFD simulations. By moving to a short overview of how does it work, we can do this. We can do in this way. So we have to define, according to the adaptive design procedure, a specific function, which is the actual reaction rate. So basically, in this specific function, which is written in the Python languages, we have the interface for the kMC or the microkinetic model. So we basically provide the information on where we have to compute the kMC simulation, for instance, with Zacros, or to solve the microkinetic model, how to post-process the result and get back to the system the relevant information related to the TOF, to the coverage distribution, to what we need to tabulate. So if, for instance, we would like to tabulate the system that Matteo Maestri showed today, so the kMC oxidation over ruthenium oxide, for an isothermal simulation at 600 Kelvin with the partial pressure between 10 to the minus 6 and 10 to the minus 1 for both CO and CO2, we can start with an initial dataset which is discretized with 3 points for each species. At this point, we have to properly set up, according to the procedure nomenclature, the input file for the adaptive design procedure. First of all, we have to define which are the forest parameters, and these forest parameters control the machine learning algorithm. Then we have the algorithm parameters which tune the effect of the various features of the adaptive design procedure, and you can play with them in order to understand how does your system react to this system. Then, after the specification of the name of the various files, so where you would like that your surrogate model has been saved, and if you have eventually some benchmark data, some query data in order to validate your final model, you have to specify which are the independent variables. So in this case, we have CO and oxygen, which is the range of the variable, and then the way in which we would like to acquire those information. So basically, we realize that for kMC simulation, it's much more better to save all the information in a logarithmic form rather than employ the linear variation, since the strong variation by order of magnitude can be much well described by using a logarithm or as acquisition function. You can choose logarithm, linear, or inverse according to the different variable that you have to consider. Finally, we have to define which is the tabulation variable, and the tabulation variable in this case is just the system TOF tabulated by using a logarithm acquisition function. Okay, now we have everything ready. We can initialize our model, our design procedure, and we can train it. And at the end of the procedure, we will have a machine learning surrogate model in terms of extra trees. And this model is being saved in a pickle file, which means that you can copy, transfer, share with your collaborator and archive. And more importantly, you can also couple with reactor and CFD simulations. How does it work, the evolution, the construction of the procedure according the construction of the dataset according to the design procedure? Well, we start at time 0, iteration 0. We have our 9 points, 3 per species. And then we move at the second iteration to 5 per species, since we need to add all the intervals due to the requirements of the specific fashion of our function, which has this very strong peak here in this region of the composition space. And then the iterative procedure continuously, unless we reach our termination criteria with this specific distribution of the training point. You can clearly see concentrate the position of the dataset close to this peak, where the function actually changes its slope much more importantly. As a whole, here we have a benchmark which reports the TOF calculated on a benchmark dataset, so a different dataset, not the one we employed for the training, on a different dataset by using kMC model and by using the extra 3 simulations. And we have a very good agreement with deviation which are not larger than 15%. So why we have an improvement in the accuracy and time due to the procedure? Here we compare the performances of different evenly distributed grids with 144 points and 400 points. With the adaptive design procedure, we end up with 100 points. If you focus on this picture on the right, we can clearly see that the same amount of points that we have in adaptive design procedure in an evenly distributed grid, so which doesn't follow the function trend, increases the scattering of the points, which are usually farther from the parity line. So even in this simple system with those 2 species, this improves the performances of our simulation. Moreover, we have also that the adaptive design procedure strongly cut down the computational burden related to the generation of the computational domain. If I have to run 400 kMC simulation, I end up in some days of overall cost. If I'm going to employ the adaptive design procedure, I achieve the same accuracy by using roughly the 65% less computational time. This, the envisioned approach, can also be extremely more beneficial if we move to systems with higher dimensionality. So if we move to the microkinetic modeling on water gas shift by using rhodium catalyst, which Matteo showed before, we can clearly see that we have a strongly reduction of the computational burden, since we are going to employ 30,000 points less with respect to the evenly distributed grid. But how can we achieve this? We can achieve this since the combined action of the machine learning features, which enable us to understand which are the most important variables, and the simultaneously positioning of the points according to the function behavior, enable us to describe properly the system, reducing the number of points in the direction which are not affecting our calculations. Very briefly, at the end, I can show you how we can introduce these models into CFD simulations. So let's consider the same case that we have seen before. So our 4-sphere string reactor. We have a 5:1 mass fraction. We have a 5:1 ratio of CO to oxygen, so it's a CO-rich simulation with 5% of CO at the beginning. Same flow rate, but an isothermal simulation at 600 Kelvin. Now we're going to employ a kinetic Monte Carlo model of the oxidation of the ruthenium oxide, which consists of 3 gas species, CO, oxygen, and CO2, 2 adsorbed species, adsorbed CO and adsorbed oxygen, and 2 different types of active sites, which can be both either bridge or CUS. If we run the solution exactly with the same physical model, but just by changing our kinetic scheme from the microkinetic model to the machine-learned surrogate kMC system, we achieve the following distribution in the gas phase for oxygen, CO, and CO2. So basically, we are able to properly account for the distribution of our species inside the reactor according to the kMC chemistry. And moreover, we can also understand the actual TOF on each position on the catalytic pellet. And I would like to emphasize that according to this specific kMC scheme and according to the behavior of CO oxidation or ruthenium oxide, you can have very sharp transition in the activity, which moves from 10 to the minus 6 to 10 to the minus 3 kilograms meter square per second in very short distance along the catalytic pellet, making very important the capability of a spatially resolved description of the chemistry inside this system. Finally, CFD plus kMC is not confined to very simple geometry. So we can also extend this kind of concept to whatever complex geometry. In this case, we are reporting what we have published in our recent work on chemical engineering journal, the simulation of this system in a very three-dimensional complex geometry as the one of an open cell foams. And I would like also to stress that the tabulation via machine learning is not confined to the reaction rate. We are not just, we have the capability of tabulating whatever important variable that you need. So we can also tabulate the amount of the adsorbed species obtained by averaging the kMC results, but we can also tabulating the different speciation of the absorption of a species to a specific site. And this means that we can fully retain all the chemical relevant information which can be provided by the kMC simulation, also at the macroscopic level of the computational fluid dynamics in the solution of the chemical reactor. Okay, so I have finished my talk, and I thank you for your attention, and I get the stage back to Matteo.
Thank you, Mauro, for the very nice presentation overview. I think, in the sake of time, I think we have only time for only one question, and then we move to the conclusions of the workshop. So there was one question related to the equation for the rate constant is different from the one derived from transition state theory. What is the relation between the two?
So basically, what you have to do is to employ the information that you get from your DFT or force field simulation in order to compute those quantities in order that to be implemented according to that specific formulation. So you cannot use in principle your results as they are. You have to post-process a little bit those ones in order to create a microkinetic model, as shown Dion on Monday on day one.
Okay, the rest are also related to some technicalities about catalytic foam. I think we're gonna reply offline, so we can provide a more detailed and practical answer. So I think we can now move to the conclusions. So I'm going to share again my screen. Is it okay, Riccardo? Okay. So this was the last day, and we, on behalf also of all of the organizers, we want to thank you for your interest and for the great success that we have, because we have quite a substantial number of people that attended live or within retention time the event, beside also quite a substantial amount of registration that exceeded the 550 people registered to the workshop. What I want now to ask is the other organizer to a brief comment about the workshop, and then I will give you also some practical aspects related to some of the questions related to videos and materials, and then we're going to conclude. So Dion, if you want to say something.
Yeah, so Matteo, thank you. Thank you everyone for organizing and putting this together. This takes effort to coordinate from our side. Thanks for the participants. Looking back at day one, we got a large number of questions indicating the interest. We have actually answered all those questions. We are going to provide this, together with the slides after, the workshop. We'll make this available also, on the web, website. Professor Maestri has put together some questions. We'll be very interested in learning from you about what you liked, what you think can be improved, how we can do, better, how we can serve the community, better. I think this is important to us. It's important to all of you. This is how we make things, better. So thanks again for attending and for all your stimulating questions. Looking forward to another interaction like this in the future.
Thank you, Dion. Gerard, if you want to say something.
Yeah, sure. I'll echo what Dion says. Thank you for inviting us to the workshop. We really enjoyed doing this. Anyone who's interested in any of our software packages, PMUT, PGRAD, OpenMKM, RenView, my contact information is on GitHub, and you're welcome to contact me if you need some thoughts on how to access the software, how to use it. So looking forward to hearing from people.
Thank you. Michael?
Thank you, Matteo. I also echo Dion and Gerhard's comments. So it's been a pleasure participating to this workshop and answering your questions. I saw that some of you actually have downloaded Zacros. We saw a bit of a spike in the request for licenses yesterday, so that's good. I encourage you to look into the material that was made available online, and also the material that was already there on the website of Zacros. And of course, if you have any questions, feel free to contact me. And I'd love to hear from you about how you're using Zacros and also the other software packages that were presented in this workshop. So thank you very much to the organizers and the people who participated to this.
Thank you, Michael. Mauro?
Okay, I would like to say that it's a real pleasure to me to be part of the organization committee of this workshop. I think that we achieved a very good result in providing information from the micro to the macro scale, and I also think that it will be important to get in touch with all the people which have been participants of this system in order to get their feedback to us and to tell us if they are going to employ our numerical packages in order to make their research or industrial activity in order to improve them every time more to reach all the information and features that we need. I finally thank all the people which are involved and Matteo for the opportunity of setting up everything together.
Okay, thank you. I want also to thank all the people that help also for the technical organization. So there was an effort also from technician from Politecnico di Milano that made possible the live meetings, and also I would like to give a special thank to Riccardo Ietti, that I already mentioned him in the previous slides. He's a PhD student from my group. Also help us today and in these days to manage the control room. So thank you, Riccardo, for your help in this service. With this, as also mentioned by Dion, I will send you now an email with a brief survey. We will be very grateful if you could fill it, because it is important for us to hear your opinion in order to make also in the near future, additional workshop that can also be more in line with what the community wants. And as also anticipated by Dion, I think this is a great service for the community as a whole. I will send you also in the next few days an additional mail with all the materials. So basically the presentation and all the material that the different speakers want to share with you. So you will find some links so you can download it and then keep it in your records. And also I will let you know where you can find and you can have access to the recording of the whole workshop. So from day 1, day 2, and day 3. With this, I think we can conclude. Thank you again, and I hope to meet you soon in person somewhere in some conferences around the world. Thank you and goodbye.